Welcome everybody to the channel, MC Tune, where it's always Tuesday night. Even though the calendar says Wednesday, and maybe even Thursday for some people, time travelers and all, it's Tuesday night here. I will be debating Flatzoid in a minute here. He's almost ready. He's on Zoom. We're going. And but I got to read something here. Professor Parks, PhD, said for $5, why do you insist on having these off-day debates during the middle of my workday? What about my needs? This is I try to make everybody happy, but you can't make everybody happy all the time. So, Professor Parks, apologies. You'll have to suffer through it. And David Lee is a new member. Thank you for that. And I've got these swapped here. Hold on a second. Let me get something. There we go. How about that? There's Flatzoid. And hello, Flatzoid.
Again.
Aloha again. We were talking before a little bit, in case you don't know. So this is for those watching on my channel and on your channel too, Flatzoid. This is my monthly one-on-one because I'm a patron at the what level? Wolf something level?
Yeah, Wolf.
All right, now
Thank you, Wolfpack.
So that makes me one of Wolfie's 60/20s people then, right? Is that what you
No, we flat earthers. I got 6 Patreons, you one of them, so that's awesome.
Hey, how many people are in your chat right now? Watching right now?
60, I think.
Shame on you. All 42 that are not.
I got a lot of members at least, so.
All right. You can't. How is it? You just think about this, people over on Flatzoids. How is it that I'm a better patron than you are? All right. Okay. This is the monthly. We missed last month because I just didn't have the time, but now it is.
Yeah, we're very busy. Yeah,
it's time. So, the topic.
But you've been debating a lot lately.
I have. Well, the challenge with you, of course, is your time zone is a bit of a challenge. So.
Oh yeah, definitely.
So, all right. Well, celestial navigation is the topic.
Mm-hmm.
And I got my book right here. This one here from David Birch, Celestial Navigation. Do you mind if I cover a little bit of something first?
Yeah, go ahead.
All right. Let me get. I'm gonna. Let's see. I'm gonna change it so people can see what I'm talking about. Where is it? That's not it. There it is. Okay. So I'll share to you what it is that I'm doing, and then you can present it if you want to your people there too.
Okay.
And it's a little skewed. There we go. All right. Here we go. All right, you see that?
Yes, I do.
All right, that's Euclid's Elements, Book 3, Proposition 18. So that shows there on a circle, which when you bisect a sphere, you get a circle. That from FC, that's from the center of the origin of a circle out to C, a point on the surface. That intersection between FC and that line, that straight line, is perpendicular, showing that a curve can have an angle to it at a perpendicular point. And that another line there from F to G, do you see that F to G line?
Mm-hmm.
That F to G line is not perpendicular to line ED, but it is perpendicular at the surface B, at the point B on the surface. One thing to note, because sometimes this comes up, is that the fact that there is a straight line involved does not change the fact that there's a curve on that circle, right? That circle is still a circle, even if there is a straight line involved. They are independent of each other. All right? They have a relationship, but they are not, one doesn't, the fact that the line is straight doesn't change the fact that the circle is curved, right? Here is, all right. Here is then another thing that sometimes comes up is whether or not you can measure an angle to a curved surface. And that goes back to that previous one. I'll just show this here. I'll talk over this. There's a exercise ball that I have there, and I used the Theodolite app on my phone to measure an angle. You can see me holding up that phone right there to the surface of that sphere. Right there, right to the edge of it. And that's going to represent that line right there, that view. That's going to represent line from position G to position C on this diagram here. That's what we're seeing at this right here. And then we move along, and the angle to the top of the rocket there is what I'm measuring. You can see it's 15.9 degrees, and if we go back a little bit, we'll see that the angle to the surface of the ball there is minus 28.6 degrees. So you can do the math on the total angle there that I measured. So, and then one more thing, here is our conversation so people know. I asked you, and you didn't clarify. I said, I'm asking, could you clarify, since this interaction has left me wondering, do you claim, 1, celestial navigation is possible using only flat Earth, or 2, celestial navigation is not possible using only flat Earth? I asked you that, you didn't answer it, and I even said so number 2 because you didn't answer it.
There
And
we
you
go.
didn't
It
answer
is
that.
answered.
So
It is there. It's flat Earth based. There we go.
it's
That answered.
okay. So number 2. Are you saying that it is
number
possible?
Number one, it's only possible for
Ah,
Earth.
it is possible using
Yeah.
only flat Earth.
It's because it's flat Earth based, yes.
Okay, so
Even what you just pulled up shows it's flat.
this shows that it's curved, actually, though. Just like this shows that that's
Mm.
curved, right? So there's an angle to a curved surface right there.
Can I quickly correct you something you just showed there?
Sure.
You said take an angle to the surface. Note that when you do celestial navigation, you're taking an angle from the surface.
No. When you do celestial navigation, just like on this one here, the phone is not actually touching the surface. Like the camera is not. The phone was, but it's above the surface. Right. So
Yeah,
so
but
again,
when you're on a boat, when you're on a boat,
yeah, you're
you
above
are
the surface.
on
Yeah.
the
So like
surface.
so like point G, when you're on a boat, you're not half submerged in the water. You are at point G on this diagram when you're on a boat, or at any elevation above the surface of water. So in order for it to be on the surface, the camera would have to be half submerged in water. Anything less than half submerged in water is going to be represented by point G on this diagram here.
Okay, now you're above the surface.
Yeah, above the surface.
Okay, and your point is?
I'm just saying, just for clarification, so that there isn't a confusion later, when I'm doing this measurement here, the camera is at point G on this diagram.
Mm-hmm.
Okay.
Okay, so you're saying it's just above the surface. Okay.
Yeah, it's above. It's not touching the surface, like half submerged in the surface.
And can I ask you why you got straight lines there?
Why do I have straight lines?
Mm-hmm.
Versus what?
Because when you do celestial navigation, you would agree that you're losing optics, so it's refracted. So
Very,
it's not a
very
straight
true.
line.
Yep. So this is the first case to increase the precision. You can use refraction adjustments, but when you're just dealing in an introductory level here, which is where we're at right now still, then you can use first order approximations by not including the refraction.
Yeah, but that's what I'm
So-
saying. You guys require the straight line to make the angle measurements, which means it's flat. Your
Mm.
horizontal reference datum is based on a horizontal.
So again, no, earlier
from being above the surface.
yeah, but
Not in
Flatzoid
the
earlier.
not in the center. 'Cause
Yeah.
you
Let me
already assuming you need to be in the center of the Earth for this, correct?
no.
That's why you're using it from the rational horizon.
No, you're using it from point G, not point F.
Yeah, but point G would be the sensible horizon, correct?
Point G, no, point G is the location of the observer.
Okay, and that is the sensible horizon because that's with the height of I.
The height of I.
Which is just sensible horizon.
Okay.
It's
Yeah,
parallel
you can use
to your
whatever name you want for it, but the fact that line GC is straight doesn't change the fact that the circle is a circle, right? You agreed to that earlier.
yeah on
Right. Okay.
geometry, yeah, that's
Yeah.
true.
So,
But when it comes to celestial navigation,
uh-huh.
you're not living in a two-dimensional geometric shape.
Well, of course not. And like I said, when you bisect a circle, you get this. Or sorry, when you bisect a sphere, you get a circle like this. So that's what we're doing here. So
Yes,
that's
what I'm asking.
again, that's what this is.
When it comes,
Yeah, and
that's
this
what I'm
is
asking when
again.
it comes to your celestial sphere, out to your nautical celestial observations, you require straight lines, which you don't have because you said refracted. So
No,
it's
I
bent.
don't.
And you require line of sight to the GP of the star. So that means
no, actually no.
yes, that means the horizontal has to be
Flatzoid.
that's what a circle of equal altitudes
Flatzoid.
are.
Can you do celestial navigation?
Yes, everybody can. It's called navigational observation.
You
and
can
using a nautical almanac, yeah.
You
but
can.
we're not doing
But you can't.
what we're doing
But Flatzoid, I know that you can't do it.
obfuscation.
Why are you saying that you? Why
listen,
are you saying that you can do it? I know you can't. Flatzoid.
Listen, obfuscation. Do you
It's
have
not,
straight
it's
lines?
not obfuscation. Right here, Slit. Right
Do
here.
you have straight lines?
Can you take these 3 points here
Do
and
you
get
have
the
straight
observer's
lines,
location?
McToon?
No.
Do you have straight lines, McToon?
Hold on. You cannot do celestial navigation.
Do you have straight
Flatzoid.
lines, McToon?
Flatzoid.
Do you have straight lines? You
Oh.
haven't answered me. Do you have straight lines?
No,
McToon?
they're curved.
Then you can't do celestial navigation.
Of course you can.
Because
Of
celestial
course you can.
navigation requires straight lines.
No, it doesn't. No, it doesn't.
You're showing on screen straight lines.
I am, like I said, a first order approximation. Do
So
you not know
what
when I say a first order approximation, do you know what I mean?
Go ahead, explain it.
Okay, that means that when we do an introductory level to this and our precision isn't as good as it could be, then we use these first order approximations. Then as we progress to more and more need for precision, then we'll include the curved line, which of course is totally possible. You can totally do a curved line.
But the angle measurement is a straight line, correct?
No. Not when you include
not a straight line.
No, when you include refraction, you're just talking about the intersection.
When you citing the star or whatever, you don't have refraction in taking into account. You're just citing it, correct?
Yeah,
you're looking at
as you increase
taking an angle measurement.
Hold on, I'll answer. You asked me a question. When you take that angle, then you adjust that angle with the refraction if you want to increase your precision.
After you've taken the angular measurement, correct? Which requires straight lines.
No, it doesn't. The angular measurement does not require a straight line. Like we see here.
You're showing it on screen. You're showing it on screen with straight lines.
Yeah.
What's an angle, McToon? What's an angle?
Yeah, an intersection between two straight lines. And you can have hold on. Let me finish before you interrupt me. You can take a tangent to a curve and use that as your straight line. You can use 2 tangents to 2 curves and use those as your intersecting points and get an angle at those two.
The GP from the star has to be on the same plane as the GP of the observer.
No, it doesn't. No, it doesn't.
Yes, it does.
No, not at all. Now, again, I am the only one of the two of us that can actually do celestial navigation. You can't. I've gone through this book. You cannot do celestial navigation. You've admitted that. Right?
What's a circle of equal altitude, McToon?
Feel free to disprove me by showing the process of doing celestial navigation.
What's a circle of equal altitude, McToon?
It's all the points on the surface of the globe that have the same angle to the star.
So same 90 on the same plane?
No.
So if I take an angular measurement to a star, what is that? Where does the top line go to from observer to the star, correct? Of the angle, the top line.
From the observer to the star. Yeah.
Okay, where does the horizontal line go out to?
The surface of the Earth. In this picture, it's line GC.
No, sorry. When you're taking a line of sight, it's to the GP of the star, Mattoon.
No, not at all. Not again. I've done celestial navigation. You have not. I know what I'm doing. You do not know what I'm doing. So that's not how it's done. I mean,
So
I can we can go through. You've conceded what?
So you've conceded then
I've conceded
require
nothing.
straight lines. You require
No.
straight lines for a measurement.
No, I've
And
conceded.
you don't have straight lines because
Flatzoid.
of refraction.
Flatzoid. I have not
And you
conceded that.
conceded you
I have
do
not
not
conceded
go
any
to
of these
center.
things. Why do you just lie about this?
You're telling me
I've
you
not
know what's
conceded
going
any
on,
of
but
these
you don't know
things.
what a sensible horizon is.
So,
What's a sensible horizon?
there's lots of names for the line GC.
What is
I'm
the
just
sensible
gonna
horizon?
say the line GC. Right? Or do you
No.
mean the line
The
GC
sensible-
in this
the
diagram?
sensible horizon is the horizon that is parallel through the scope of the sextant. What is a visible horizon?
Go ahead.
That's the horizon you're measuring to when you're taking the GP of the star.
There's no GP of the star. Tell me what page of this book talks about measuring the angle to the GP of the star.
The Nautical Almanac is based on the GP of the star.
No, it's
you know,
not.
when you're looking at the
I'll-
almanac and it
I'll
says
need a-
Aries,
I'll-
and it says Aries, and it gives a
Yeah,
GHA and a declination.
Yeah, but that's
of
not
that
the
star.
measurement of the angle that you're doing with the sextant, though.
That's the
Flatzoid.
GP. That's the GP
Yeah, it's the
of
GP
the
of the
luminary you are observing.
Yeah, but that's not what you're actually looking at when you're
What's a
measuring
geo-
to the
what's-
horizon.
What does a geographical position mean?
That would be the point on the surface of the globe directly underneath the star at that moment.
Great. So when you open your Nautical Almanac and you look and it gives you the GP of the star, that's the geographical position on the surface of Earth, correct?
Of the star at that instant, yes.
Great. So that GP of the star is on the same circle of equal altitude of the observer, correct?
The GP of the star is the center of the circle of equal altitude.
Great. So if I measure a star, let's say, and calculate it 3,000 nautical miles away from me, it's straight on the same plane, a
No.
horizontal plane.
No.
You said you know how to do nautical navigation. You're
Oh, I do.
literally throwing away nautical
do.
navigation, yeah.
Oh dear, no. Oh no. Not at all.
Yes, you are.
That's not how it's done though, Flatzoid.
Oh,
Because I
so you're saying there's no trigonometry then for celestial navigation?
didn't say that. Why would
So
I
you
say
would agree
that?
there is trigonometry for you say we use triangles, a trigonomic
Oh no.
function.
No, there's no
So-
triangles. There's no triangles used. No.
What if I bring up a whole bunch of citations saying you're wrong? Would that prove then you don't
No.
know how to do celestial navigation?
No, what it would do is it would show that you know how to cherry pick.
Okay.
So
that's
what I want you
checking-
to do,
okay.
if you were
I'm
to
gonna
show
share
me
my screen.
the step-by-step process of doing celestial navigation, that includes a triangle. That's what you need to do.
Sorry. Can I bring up
So that you can
some
cherry
of those
pick.
citations for you?
Sure. Cherry pick away.
Cherry pick. It's not cherry picking. It's
Oh,
just
you're
simply.
totally gonna cherry pick. I mean, we all know it. We all know you're gonna cherry pick. But go ahead.
Okay, I'm gonna just pick up some of them quickly. Open them for you. There's no cherry picking, but okay. Because you clearly say there's no trigonomic function for celestial navigation.
No, I said there's no
correct?
triangles. So try to
Well,
keep
what
it
is-
correct.
what is
There's no triangles in celestial navigation.
so? What's trigonometry?
Trigonometry is more than just triangles. You don't know that?
What's trigonometry? What's trigonometry?
What is trigonometry? You don't know it? Why are you trying to tell me what trigonometry is if you don't know what it is?
You're saying it's not triangles. I want to know what's.
I said
what's
it's not
Sakatoa?
just triangles.
Is Sakatoa triangle?
SOHCAHTOA is, but there's more to trigonometry than SOHCAHTOA.
3, 4, 5, 6.
It's not just solving triangles. Do you know how a fast Fourier transform works?
No, go on.
Okay, sine and cosine are used in that. No triangles at all. Do you know how discrete cosine transforms?
But you see, we're talking about celestial navigation, which specifically works with trigonomic function
Oh,
of
well-
Sakatoa.
It does. Oh well, just show the process. Go ahead.
Let me quickly get on screen. Can I share my screen? Okay. Let's just clear my screen up there. Share. Okay. You can see what's going on here.
Not yet.
Okay, I
It's-
don't need this one yet. This is just the principal six. I'm going to bring that up just now. Okay. Navigation of the stars. Okay, this is obviously different techniques. Talking about trigonometric was first used in navigation by 14th century. Several navigation techniques can be identified in navigators' personal notebooks, including the table so the application of plane trigonometry. You would agree plane trigonometry requires it to be a triangle.
No,
What's plane trigonometry?
don't know that it's not specifying it here. It's just giving a little bit of a
Plane
overview.
trigonometry requires it to be on the same plane, in other words. So if I'm making an angle measurement over a
Okay.
plane,
Well, bring up the
horizontal.
process. Let's look at the
Okay.
process they used.
This is one navigation
up.
of the stars.
Yeah, bring it up. Bring up
Trigonometry.
the
One,
bring
I'm
up
bringing next.
no, bring up the process
Don't
that they
worry,
used
we're
in that.
still getting there.
Wait,
We're
you're a
still
little.
getting there.
Why are you scared to bring up the process that they used?
We're still getting there.
See, you're just cherry picking.
processes.
You're proving me right by cherry picking.
Trigonometry process or celestial navigation or astronavigation subject presentation of maths
Well,
curriculum. Blah, blah,
Bring it
blah.
up. Let's look at how it's done. Bring
I'm
it up.
just first giving all the citations showing that they do
But-
use trigonometry.
Well, just show how it's done there, Flatzoid. Let's look at how they do it.
Trigonometry.
Why don't you want to show how it's done?
Sailing with trigonometry.
Let's
Okay.
bring it up. Come on. Oh, you don't want to bring it
I've
up.
got it up. Trigonometry. is
No,
used in
bring up the
navigation.
process. Bring up the process. Let's look at the process, and we'll check
You're
it out.
saying we don't use trigonometry. I'm saying we do use trigonometry. That's
Okay.
the argument.
I'm
So
happy to go through the process in this book where there are no triangles involved. But you're saying there's triangles involved in the process, but you're not showing the process. Go ahead, show it where it's happening. Can you show
cosine.
show the step-by-step process of celestial navigation using triangles? Go ahead.
Okay, you take a measurement to the celestial object, correct?
Go ahead.
An angular measurement.
You don't need to keep. You don't have to
I
keep
think I'm gonna
asking me.
draw
Just go ahead and show the process of
I'm
doing
going
celestial navigation.
I need you to concede when I do these things. That's why I'm doing it this way.
No.
Yes, yeah. Okay. When we take a angular measurement to a star, let's say in the sky here, we are on the ocean floor or on a ship or whatever, it doesn't matter. Using a nautical sextant, so obviously on a little boat. Okay. And we're going to take an angular reading to the star, correct? Would you agree about that?
Keep going.
Okay. Now we got two straight lines going out that way. You would agree that we have a 90 degree.
No. That's not 90. That's less than 90.
We don't have a 90.
That's not 90 there. No, that's less than 90. That's maybe.
That's not 90.
Oh,
That's
there
90.
it is. Okay, now it's 90. Yeah.
We have a 90. Okay.
Yeah, at that point. Yeah.
Great. And the star has a 90 as well, correct?
That's it. That's presuming what you're doing is presuming that the earth is flat.
No.
You're making an
that's how it's
assumption.
working.
You're making an assumption on
is-
this.
This is how the trigonometry works, mate.
So you say,
Let's-
but this is just your claim. You're
let's-
not actually showing the process of celestial
let's-
navigation from
let's
a
say-
citation that you brought up. You're just
let's
just
say-
inventing this process that is not based on the books that you were referencing.
Let's say I measured an angle to the star at 50 degrees. Okay?
Okay,
You'd agree that's 50 degrees. Okay, to the star.
not to scale. That's fine. Yeah.
But yeah, it's not to scale, obviously.
Yeah.
Okay. We measured 50. What's the internal sum of a triangle?
180.
180.
Yeah.
So that would give us 40, correct?
Yeah.
Okay. So if we use the math anyway to just verify this, 90 minus the measured angle gives us the altitude, the elevation angle, which is 40 times 60 nautical miles, which gives us our distance. So because I did this, I was able to get the distance from my GP to the star's GP. You get what happened now.
Where did you get that 60 from?
Nautical miles
Yeah, but where did you get
Based
that
on- from the angular reading.
But
It's
no.
a segment of a circle
Segment of what circle?
of the sextant's angular reading circle. You know
But-
what
no,
a
but-
degree is?
But
Like you
yeah,
get a
but where
minute
did you get
in a-
60 nautical miles from?
The sextant itself.
The sextant doesn't measure miles; it measures angles. Where did you get the 60
Angle.
nautical?
What's an angle? What's the angle? What's an angle on a sextant? What's an angle?
It's just a certain angle. That's just an angle.
Ah, so okay.
So I'm asking you again, where did you get the
I'm gonna show
60
you, I'm gonna
nautical
show you.
miles from?
I'm going to show you. Let's look at a circle quickly. Is this circle segmented in 360 degrees?
Yeah.
Great. So that's where you get a degree, correct?
Yeah.
Should we go look
And
how a sextant looks?
what's the
Should we go-
circumference? Hold on, what's the circumference of that circle?
360 degrees.
Yeah, but what is it in linear units? Let's use
What do you mean?
let's use 21,600. Write that down for the circumference.
You're just obfuscating from my point, but anyway, like
You
I
don't want
said, let's look at the sextant quickly.
What you want to do?
I just want to show you, because I want to show you something, because you obviously don't know how a sextant looks, because if you did, you would know why you get your angular reading. Let's get a nice one. This one should be fine. What is this arch in the bottom here?
That's where you read the angular measurement.
From the index arm, correct? The index arm goes along that arch, correct?
Yeah.
Great. And is there angulars in degrees readings on that arm?
Certainly, yeah.
And then the micrometer gives in seconds, correct? Minutes and seconds.
Minutes and seconds, yes.
Great. So tell me, what's the shape of that arc that it's following, Mattoon?
It's an arc.
Great. So an angular reading from an arc.
Yeah,
based
angle,
on a.
angle. All these are angles, okay.
Do you know what the principle of a sextant is?
Yeah, it measures angles.
Angles in succession.
It measures angles. That's all it just does. It just
Angles
measures
in
angles.
Do you know what an angle in succession is?
It's just measures angles. That's all it does. It doesn't do anything special with
Do you
it.
know
That
what
would
an-
be the process that you apply to it later if
Do
you
you know
want
what
to
an
talk about
angle-
something.
Do you know what an angle in succession is?
Oh, do go ahead.
The principle of sextant is when the ray of light is reflected from two mirrors in succession. You know what succession means, right? In the same plane.
Uh-huh.
Okay. Then the angle between the incident and reflected ray is 2 times the angle between the mirrors. You know what why this is?
Yeah. Okay. So then what? All that we've done so far is measure an angle, which I don't
Using
disagree with. I completely
using
agree.
straight lines,
I completely
using
agree that
straight-
you're measuring an angle. So then what?
using straight lines parallel.
No, not necessarily. There's no requirement that the light ray coming to you has been straight between the source and your eye. It could have been curving along because of refraction along the way.
Sorry, an angle requires 2 straight lines, not a curving line.
Yeah, again, I covered this earlier. That's why I brought up Euclid Book 3, Proposition 18.
Which showed straight lines.
It shows, at an instantaneous tangent. That's what it's talking about. But it is an instantaneous tangent to a curve.
Okay,
So when you're
okay.
measuring an angle with the sextant, you are measuring the instantaneous angle. You don't know the path that it took to get there yet.
Oh, that's false. You do know the path that it takes to go, because
The sextant has,
align-
but the sextant has no knowledge of that. It doesn't have any application for the path of the light.
the mechanics behind the sextant requires you to know the angles of the light. That's what the angle in
But I'm not talking about the angles.
You know what the law of,
I'm talking about the path that the light took from the source to the eye.
You know what the law of reflection is?
The law of reflection. Ooh, that's a good one. Let's hear it.
If the angle is coming in,
The instantaneous angle,
the reflection is going to be equal. So if it's got an equal angle coming in on this mirror, it's going to have the same equal angle reading on this mirror. That's why it's angle.
Yeah, okay, so it's angles. So you still haven't answered where these 60 nautical miles came from, and that's what this whole thing is about.
I did answer it. It's based on this index arm arc at the bottom.
Is that arc 60 nautical miles long?
It's 120 degree usually index.
Okay, but where did the 60 nautical miles come from?
Great, that's where it comes from. Let's say
where? I'm sorry, where? 60 nautical miles. Where did the 60 nautical miles come from, Flatzoid?
That's where it came from.
Where?
The angle over the arc.
Sorry, nautical
Based
miles
on
is a
true
linear. That's a linear distance, not an angular
That's your-
distance.
That's your linear distance, mate. Because you're measuring over a celestial sphere,
But
correct?
well,
Does
yeah,
the
that doesn't.
celestial sphere
That
does
I
the
don't know why you
celestial
want to bring that up. That's a little
Does-
shooting yourself in the foot there. But
does-
okay,
no,
okay,
the
celestial sphere. I love it. Celestial sphere. Then what?
Celestial sphere is based on perspective. Anyway, the
Ooh,
celestial
that's a
sphere,
new claim.
the celestial sphere closes the arc of the tangent.
That's an interesting claim. Okay.
It's not an interesting claim. It's the truth, mate. What's the maximum angle for the sextant? Let's put it from the vertex of that index arm mirror.
The maximum
what's
angle?
The maxima from the left to right. Yeah.
I don't know. It doesn't really matter, does it?
Yes, it does. It means it's 60.
You got that
Yeah.
right. You got that right this time there.
Sextant, a sextant. It's a
you-
section of a.
You've got burned on that before, haven't you?
Sorry, a section of what?
All right. So I'm still wondering where the
What
linear
is the
number
60?
comes from.
Listen, what is the 60 degrees? A section of a.
60
Circle,
degrees is
correct?
a section of circle. Yeah, absolutely.
Great. So the sextant, aka the section of a circle,
Uh-huh.
that section is taking a measurement of that arc on the bottom. You see of the sextant itself.
Uh-huh.
That's your degree measurement.
Yeah.
That's how you get your nautical miles. And guess what those nautical miles are based from?
The circumference of the globe.
Straight lines coming in succession.
No, I'm gonna need to see it, the actual measurement behind the 60 nautical miles if it's something else.
90 degrees, which is your GP, minus your
Yeah, but where did
inputted value that you
yeah,
measured.
but where did that 60 nautical miles come from?
Again,
Yeah, show us that. Go
very-
back. Look at that circle. Bring the circle back up, and then let's look at that circle again. All right, now on that circle, let's see, in order for the 60 nautical miles to work, you have to have the linear circumference be 21,600 nautical miles, right?
Yeah, and
Okay, so put that on the screen so everybody can see it.
21,
Yeah, 21 comma 600.
600 nautical miles.
Yep.
Okay.
All
Yeah.
right, that's
Now what?
that's the circumference of that circle.
Yeah. Okay.
Right. So then
So that's from the center to the outside. Yes.
no, that's radius is what you just described.
Yeah.
Circumference is all the way
Yeah.
around the outside.
All the way outside. Yeah.
Yeah.
But you're required to measure this from this radius, correct, to get the circumference.
No.
How do you get the circumference out measuring?
There's multiple ways to get the circumference. It doesn't matter though, because this is the number that you brought up.
Sorry,
60
we're talking about celestial. You're talking about
60
celestial nautical.
Yeah, but
talking
you're
about
bringing
celestial
up.
navigation.
We're going through the
Which require-
derivation of 60 nautical miles right now in the
No.
Flatzoid, right?
Yeah.
Where did that come
based
from?
On celestial navigation. Correct. The topic is celestial navigation.
Yeah,
correct?
But you brought up the number 60 nautical miles out of the blue, and I'm just asking for the derivation of that number. And
Again.
that's what we're working on here. So we've got a circle of 21,600 nautical miles. Where is that from? Where did that 21,600 come from?
There we go.
Is that a witch's hat? That's a cute witch's hat. It's got some decorations on it.
This should
How
be
how much does a witch weigh?
which go anyway.
The same as a duck?
Horizontal line
What
through the
what
scope.
other than wood floats?
Anyway, it's the horizontal line that's coming through the scope, correct?
Wait,
To the
hold
mirror,
on.
to the horizon mirror.
That's a giant witch's hat. It's like, why are you drawing the witch's hat on this circle of 21,600 nautical miles circumference?
Because I'm trying to explain the measurement comes from the sextant. This is the index arm coming down this way, okay, with the index mirror and
Wait.
the horizon mirror and the scope.
Wait a second. What you're trying to say that this witch's hat is something other than a witch's hat? Some people
Yes,
think
it's
it's
a
a slice of pizza. What kind of pizza is it? New York style pizza, Chicago style pizza,
Pepperoni.
pepperoni.
Okay, so anyway, we got the index arm, we got the horizon mirror, the index mirror, and the scope, and we got the degree arm at the bottom. Okay,
Okay.
this degree arm is usually about 120 degrees, correct? Usually,
Okay.
they all differ 100 degrees, 120, doesn't matter. But this angle is 60 degrees. Now, what's 60 plus 120?
180.
180. So making a triangle.
No.
Okay.
No. You can't take an
This,
arc and then say it's a triangle. You have an arc. You have an arc of 120 degrees or 60
okay.
degrees. What do you
take that arc at the bottom and make it a straight line? Would
Oh
you
my
still
gosh.
get degree? Would
Hold
you still
on.
get degree read?
Let me get some
degree
let me get some
readings?
tune shine in. This is just a little bit too crazy.
He's not obfuscating, guys. I'm having fun with him.
All right. So I'm still waiting. Where will the 21,600 nautical miles come in?
60 times 360.
Yeah, okay, but that's a linear measurement. Where did that come from?
I'm telling you, this arch at the bottom
Yeah?
and the celestial sphere close the circle.
Who measured the celestial sphere?
You do when you take the sextant.
Oh dear, this is new stuff. How does that work?
You stand on a horizontal baseline and take an angular measurement with two straight lines to a celestial sphere to its GP, which is on the same horizontal plane as the observer, which gives you your angular reading on this arch of the sextant.
Well, that makes no sense at all, Flatzoid. Not at all. You don't, I mean, you're not really good at geometry, are you?
Wow, brilliant rebuttal there. You're not really good at geometry while I'm literally giving the answer to you.
No, you haven't. I'm still waiting.
So again,
where is the 21,600 nautical miles from?
60 times 360 degrees.
Yeah, but where is that linear measurement done? Where was that done? What's the source of
arch, it? This arch.
Yeah, but that arch is just measuring an angle.
The angle measurement in degrees.
Talking slow doesn't help. It makes you sound a little dumber, a little more confused about this topic.
I have to talk slow because you seem to not understand this arc is in degree
measurement. It's a degree measurement. Increments. Yeah, but I'm asking where the linear number came from.
That's where it came from.
Where? The angle?
The index arm over the arch gives the angular reading, which represents the straight lines to the celestial sphere.
Okay, so we have the celestial sphere. Who measured that? And can I see?
You do with your nautical sextant.
How? Oh, well, let's see the math.
I just told you.
Let's write down the math on the screen there so that we can see how the 21,600 pops out.
90 degrees minus, let's just say we measured 50 again, like I said. And our co-altitude angle was 40.
Yeah.
And you times that by 60 nautical miles to get a distance, correct?
You do, but I'm wondering where that 60 came from. You're not answering the question. Where did that 60 came from? Where did it come from?
Because it's an 60-degree angle you are using. You see, the sextant is a 60-degree.
But 60 degrees. You said 60 degrees is not 60 nautical miles, Flatzoid. I hope you know that. You know that, right?
It's a segment of a circle.
That's right. Yeah. But and how big is that circle?
So
21,600 nautical miles. Where did that measurement come from?
60 times 360, correct?
Yeah. How are you converting from an angle to linear units? What's that? It's just that it's that source of that conversion. Where did you get that from?
I don't know how much more to tell you this. That is the conversion, because the sextant is a section, aka 60 degree of a circle.
Yeah, but you're not using 60 degrees equals 60 nautical miles. You're using 1 degree equals 60 nautical miles.
Great.
Yeah,
So
where did
1 degree
that
per
formula
60 nautical miles.
Yeah, where
So
did
if
that
I
formula
measure
come
one
from?
so if I measure 1 degree,
Uh-huh.
that's 60 nautical miles,
Yes, and where
correct?
did that
On
60
the arm,
nautical
on the
Yeah, and where
index
did that
arm.
Yeah, and so I'm still asking, where did that 60 nautical miles come from? Where was that linear measurement performed over the
Is this
surface of the
guy,
earth?
dude? I've
No,
literally
you've
said it
you've
20
literally not
times.
explained it at all. You never showed me the source of the 60 nautical miles. Never once.
Okay. Let's do it this way, man. Maybe this might make it easier for you. This is a segment. It's a 60-degree segment,
Okay.
aka a sextant. Okay. This is the arc. Oh, why am I drawing like that? This is your degree angular measurements. So you have a degree segment all the way to 120. Correct?
Okay.
So if I measured here using this and I measured a degree measurement
Okay.
on this arm,
Yep.
this is a linear angular measurement
It's
reading,
not
is
a
it not?
No, it's not a linear angular measurement. It's just an angular measurement. No linear involved there.
What's a degree
Yeah.
measurement?
It's just an angular measurement.
Is a degree measurement linear?
No,
Is it not?
it is not.
Show me
didn't-
how it's not linear.
You didn't know that?
Show me how it's not linear. Because last time I checked, a degree is always a degree apart.
Yeah, but it's not a linear measurement. It's an arc measurement.
Based on linear distance.
No. Nope, not at all.
Oh, so 1 degree is not the same spacing to 2 degrees and not the same spacing to 3 degrees.
Correct. 1 degree is different than 2 degrees, which is different than 3 degrees. Yeah.
So the spacings are different.
Yeah.
I don't
Yeah.
understand.
One
you're
degree.
confusing me now.
1 degree. Well, that's not hard. 1 degree is different than 2 degrees. Is different than 3 degrees. That's
Yeah,
pretty
because
basic there.
they're different angular measurements, but their linear relationships are the same, spaced out.
Oh, you mean from 1 to 2 to 2 to 3, 2 to 3 to 4? Those? Yeah, those are the same
Yeah.
spacings. Yeah. Those are all angular measurements, every one of them. Yeah, not a linear measurement.
So I've got a protractor on screen.
Yes.
Okay. Every single spacing is linear, correct?
It's angular. Every single spacing is angular.
And they have exactly the same distance between them.
The same angular distance? Yes.
So linear then.
So no, not linear. They're angular.
Angular is linearly distant the same, is it not?
No, angles are different than linear amounts.
Okay. So I don't understand. Because
I believe you.
yeah, because I'm saying they are set the same distance apart from each other. So that to me is linear, because if I had to take this angle measurement on the set protractor here, and I've got now on the sextant also an arc, and it gives the same angular reading measurement, that means it's linear, correct?
No. I don't know why this is so hard for you, buddy. Look, I have a protractor.
It's not hard for me. I'm trying to lead you to understand that
I'm
the
sorry.
bottom of the sextant is an arc.
So let's be clear. In this conversation, you're not the teacher. I don't know where my protractor went. I'll draw it out for you. Maybe it'll help you.
Yeah, maybe.
Maybe not.
I'm gonna stop sharing, eh? Okay. Go ahead.
All right. I'll find a new. I'm working on it. I got a new piece of paper coming.
Because it's very simple. The celestial sphere is just the top side of the angle measurement compared to the bottom of the sextant, which closes the circle, and that's
I've got
what's
it right
linear.
here. So watch this here. This is gonna blow your mind.
Yeah, go ahead.
All right. Here I've got 2 arcs. You see that? And then I got a point there. Now, this right here from the center there, there's a line. right? And then here is another line, right? You see that there? Right? Now,
And they're linear.
and this distance here is, let's call it 10 degrees approximately, right? We'll say that's 10 degrees. Right here, 10 degrees. Now, what's this angle right here?
Also 10 degrees.
Also 10 degrees. Exactly, right?
Yeah, because it's linear. And that's what I'm trying to explain
but
to
now,
you.
what's this distance right here? This linear distance from this point to this point. Let's call it A. How about that?
Okay.
Call it A, right? And the other one, this one here, let's call that B, right? Right now, those are the linear measurements of the distance between them across that arc. And so what we can say is we can say without really any challenge here that the linear amount of A is greater than the linear amount of B, correct? Okay, so these linear amounts are different based on the radius, how far they are away from the center. But the angular amounts are the same. So on your protractor, the angular amount is the same regardless of how far away from the center, but the linear amounts are different. So you're not measuring a linear amount unless you also know the radius.
Ah, so what's the radius of the sextant's arc?
It's unspecified. Every sextant can potentially have a different radius.
But it's based on the measurement on the apparatus itself, correct? Which
Yes,
makes
just an
a
angular amount.
180-degree triangle, which comes
No,
to an
there's no
internal sum of 108 degree.
no there's no triangle in it. It's just an arc measurement.
So the degrees between the 60 and the 120 doesn't make 180.
The degrees between 60.
The index arm,
Yeah.
okay, travels along the 120-degree arc.
Okay.
Correct.
Okay.
Now the sextant itself is a segment of 60 degrees.
Okay.
So what's 60 plus 120?
180.
Internal sum of a triangle, correct?
No, you found something that's coincident. They are not it is not a triangle. It's an arc measurement. Just because one part of it is 60 and one part of it is 120 doesn't mean there's a triangle involved.
I'm proud of you. So
why are you
so
so
triangles then?
This is not
triangles are not triangles then.
This has nothing to do with spherical triangles at all. I have no idea how that came up. You're super confused about this.
I just wanted you to concede something. I want you to concede it.
I didn't concede anything, Flatzoid. Why are you lying about that? Why are you lying about that? Why are you lying about that? I did not bring up spherical triangles. You brought that out of the blue. There's nothing about this topic that includes spherical triangles.
PZX triangles used in celestial navigation is not brought up here.
That's not what we're talking about.
Celestial navigation.
But that's not the type of triangles we're talking about right now, Flatzoid.
So listen what I'm saying. So you concede then if it's got a curved side and then it's not a triangle, correct?
All that I'm saying is that you are measuring an angle and nothing else. There's no triangles involved.
I showed you citation after citation showing triangulation.
But you refuse to actually show the process of it. So go pull up one of those sources and then go into the actual book and let's go over the step-by-step process that they use to do the navigation. Let's see it.
Are you able to show me on your in your book where it says you don't use triangulation?
I cannot do that. I can show you that nowhere in the book does it say triangulation. This book right here. This book here. We're not using triangulation. There's no triangulation involved. Right?
Okay.
None.
I got
none involved. Now the book, so for reference, the book I'm using, Celestial Navigation by David Birch.
Okay.
Okay.
This is from Institute of Navigation. So they actually teach people navigation. Okay.
Super. Okay.
Great. We're gonna just go through a bit, okay? Because you think you don't use triangulation.
Okay.
So in this lesson, the lesson abstract, in this lesson, students will investigate error as shown in early activities without understanding how errors can affect your position. You cannot navigate well. Introducing accuracy and precision will develop these concepts further. The students also learn about how computers can help in navigation. Often the calculations need to be navigated accurately, time-consuming, complex, blah, blah, blah. We get all that. Let's get on to where we actually want to get to the point. So we get to things to remember. Okay, we go on. These are not neither precise, it's just giving the difference in it. Tribulating machines. Okay, so this is the sextant, just trying to explain how to use a sextant. Do you want me to read that out to you?
No, I want to get to the triangulation part.
Okay, we'll get to that. Which page is it? There we go. Trigonometry review.
Okay.
Can you read that out for us?
Yeah, that's just a review of trigonometry. Go to the part where it's applying this in celestial navigation.
There we go.
What?
Give each student the accuracy handbook. Have students calculate the trig table using the sailing on an island problem.
Okay.
Have students use calculators to trig table sheets to
Well,
rocket machine.
let's look at the sailing on an island problem. Where is it?
Okay, there we go.
Okay.
Okay, that's obviously a horizontal measurement.
Yep.
I want to go where it shows with the. Where was it? I think it's further down. They're actually giving you the. Yeah, this is where you're going to work out with the refraction and everything, obviously. But notice how
you better get off that page quick.
Why? I know they're talking about orbits and stuff because this has got to do with. Yeah, this is specifically for the astronomy. But anyway, let's move to this one. Sextant corrections worksheet. Tell me what you see here.
I don't see any triangles.
So the sextant is reading using a straight line to the star, correct?
Okay.
So not a bent line, a straight line.
Yeah, I would expect that you might get into that further along in this book if it's advanced enough.
Great. Okay. So then, and the bottom line to close the angle is to the horizon, correct?
Yeah, one angle so far, not three. So just an angle, not a triangle.
Two straight lines.
Yeah, okay.
Great. Okay. And the sextant is based on a what? A horizontal in the middle. Correct?
No, it's not.
So
it's based on
horizontal.
The only thing that a sextant does is measure angles. That's all that the sextant is doing. That's all it can do.
So
it can just measure angles, nothing more.
So when you take a sight, what do you do?
You measure the angle between the horizon and the celestial object.
But how do you do that? Do you bring the celestial object down to the horizon to make it kiss the horizon?
Yeah, you use the mirrors so that you can see both of them at the same time.
So you bring the celestial object down to the horizon.
That's just so that you can measure it. Yeah. There's nothing fancy about it. You could do it with the theodolite app on your phone. You could do it.
Create a horizontal.
You could do it with a theodolite on land. Theodolites on the ocean are a bit tough because you're moving.
We're talking about a nautical sextant, not a theodolite.
Yeah. Well, I mean, it's the same thing. They measure angles. That's what they do.
Great. I 100% agree.
They
measuring angles using horizontal.
No,
Correct.
There's no horizontal necessary in it. In fact, the sextant is unaware of horizontal. It has no idea where horizontal is because it doesn't have any way to measure any vertical or horizontal component. All it can do is measure an angle between two things. The sun, in this instance, and the horizon. It doesn't know where horizontal is. You need to provide that knowledge based on your height and the refraction.
So when you bring the sun down to the horizon, you're setting horizontal, correct?
No.
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 Are you sure about that?
What you're doing is you're using the mirror so that you can measure and line up the top or bottom limb of the sun with the horizon that you're measuring.
Remember I asked you earlier if you know the difference between a sensible horizon, a visible horizon, and a rational horizon.
Well, the only thing you can see is the visible horizon, right? You can't see other things. So visible horizon is the only one you can see. And then based on your eye height and refraction, you can obtain that other one. But that's post-sextant.
So you know the sensible horizon is what your scope is her line to. So
No,
that's
no, it's not.
scope is horizontal to the
No,
sensible
not at all.
horizon.
Not at all, Flatzoid. It has no idea where that is. In fact, you can use a sextant to measure the angular distance between two stars.
Okay, I'm gonna type what
do-
is the sensible horizon for
Do you
quickly.
are you aware that you can measure the distance between two stars with the sextant?
That's what it's made for.
Measuring the distance between two stars?
Okay. The sensible horizon is the plane of the observer's position lying at the right angle to the line formed by the observer's zenith and nadir. Would that be 90 degrees?
Yeah, it's 90 from vertical.
So
Yeah, and
horizontal.
and back on my diagram, that would be line when you're at point C, that would be line ED. DE.
So that would be a horizontal then, McToon.
Yeah, it's a horizontal tangent at one point.
Okay, this is the irrational horizon, which is through the center of your Earth, which you guys
Okay.
love to go and what we call Hall's angles. And you have the sensible horizon where your eyes are horizontal outwards.
Yeah.
Okay.
Yeah, and then the
Then you
horizon,
have
the visible horizon dips from that,
so the visible horizon,
which could
is
not
what you
happen.
look out
Yeah,
to.
could not happen on flat Earth, by the way.
Oh, that's a nice claim. Please tell me how that claim can be supported.
Well,
Why
how
can it
how
not
large
Why
how
can it not
large
happen on a flat
yeah
Earth?
how large is the flat Earth there? Do you mind if I use infinite as the size of the flat Earth?
Doesn't matter.
Okay.
Does it?
Well, yeah,
Because
I can. Oh, hold on.
is
You asked me.
the water? Listen. You said you can't have it on a flat Earth. So is the water below your eyes always physically?
Right.
Neptune?
Well, I'll show you. You asked me. I will show you the math. Or I asked if I could use infinite. You said yes. Are you good with that?
Said use what you want. It's your claim.
Okay. Well, I mean, I don't want you to come back and say that I'm strawmanning your idea of flat Earth. So is
What you made an argument claiming that on flat Earth you shouldn't have an horizon.
Yeah. Well, no, I didn't say that you shouldn't have a horizon. I say that it must not dip.
Why? The water's below me. Is
Yeah,
it not on my
I'll show you.
eyes? On
right,
my
hold on.
eyes. Listen,
I'll show
on
you,
my
I'll show you.
eyes. Are my eyes embedded in the ground?
All right, I'll show you. I'll show you here. All right.
You do know you can have a horizon on a donut Earth if
All
you
right.
wanted to.
All right, here you go. You see that? There's
You
your
have to
flat
stop
Earth.
sharing.
What I'm gonna
Stop
do?
sharing quickly.
Okay. Here is your flat Earth. You see that? Right.
It's
I
a
wrote
line, okay.
I wrote flat Earth under it because sometimes people get confused. So now let's say we're gonna go the infinite plane people, right? Now we can go a different number if you prefer, but this goes back to the 1860s with Robotham, right? There's our distance. You see that?
Mm-hmm.
Right now what is
Notice
when you solve this triangle?
Notice
What do
how
you get?
the
What do you
guy's
get?
eyes. Notice how the guy's eyes are above
Yeah,
the surface.
but what's this angle here if it's infinite? Right here. What's this angle right here if it's
I don't know. You
infinite?
tell me. It's your claim.
90. Right, it approaches 90.
May I also ask you? Is that an orthographic
So there you
view
go.
or is that?
There you go. All right.
Is
This
that's
is
orthographic,
this
correct?
is from Robotham, 1860s. Okay, right there. Now he did not say that the Earth was actually infinite. He said it was less than infinite. But when you use the number that he used, and he was in the northern hemisphere, you don't get 90. You get very close to 90. The number is very, very close to 90, and so the dip of the horizon for flat Earth from looking due south from England, where he was, is about the dip would be 0.001, I think, if I remember the number correctly. So it depends on how big you think the Earth is. And of course, from South Africa, looking due south, you might have 0.002.
Sorry. What's this dip that says dip equals 1.753 times the square root of the observer's height?
Yeah, that's it. That includes the radius of the Earth in that. Don't you know
What
that?
is the 1.753?
That's derived from the radius of the Earth, Flatzoid.
No.
It's not awesome. Show the derivation of that.
Show me how that's derived from the radius of Earth.
So you brought that number up. I haven't.
Yeah,
I haven't.
I'm showing
yeah.
it's on. Yeah, you
Yeah.
saying it's derived from Earth, so that's your claim. Show me that it's derived from the radius of Earth.
All right. Well, let's in this book here. This is your book. I haven't had a chance to look at it, but I do know that the dip angle is always derived from the radius of the Earth.
No, it's not. The dip angle is derived from your height above the surface
And the radius of the Earth. Yeah, and the radius of the Earth.
surface, not radius, surface.
Both
of the
your
Earth.
both your elevation above it and the radius of the Earth.
Height of eye correction is to bring your eyes to the horizontal
Yeah.
plane
But it
of the
includes
Earth's surface.
Flatzoid.
Because
You're gonna need R for
because
that. Flatzoid,
your
you're
eyes-
gonna need
you
R
don't
for
need-
that.
okay, show me
You-
R for a
you
horizontal
have-
line, please.
You have to include R in that number
Show-
there.
Show
One
me
point-
R for a horizontal line, please.
It's not a horizontal line. It's a dip.
It's a horizontal. You're bringing your eye down to a horizontal
Yeah.
line.
Yeah.
plane.
And how did that dip happen? What's the derivation of that number? I bet it's on
How did
the
the
I
dip-
bet it's on the previous pages. Scroll back a little bit. Let's have a look where they got that number from.
How did the dip happen?
No, go ahead.
Let's
Scroll
see.
back.
Your
Scroll back.
eyes.
Scroll
your
back.
Eyes.
Come on, Flats.
Your eyes.
Why don't you want to scroll back?
Your
All right.
eyes were
All right,
not.
you're. It seems you're a little scared to scroll back. All right, navigation,
What does that say?
educational lesson.
I'll get it for you now. What does this say?
Oh no,
What does that say, McToon?
I'm.
We've
I
first
am. No.
We've
I'm
first
gonna
gotta
pull
finish
up
one
this.
thing
I'm
that-
gonna pull up this thing that you don't want to look at.
We're
This is
first
this is awesome that you don't want to look
See,
at
this
it.
is why this is why you call dishonest. We're busy with a subject, and you want to totally
No, no,
go and
No,
obfuscate. to
you
something.
you brought up a measurement, or you brought up a number that embeds the radius of the Earth in it.
No, it
That's you're
doesn't.
gonna require R. Well, then show us the
The
derivation.
horizontal doesn't require R.
Show us
It's
where that
your
number
height.
came from.
Listen, what does it say? Height of
Outreach
eye above
slash
the sea
upload.
or ground.
/ lesson 4. All right.
Remember that 1.7 is in meters, correct? Okay, not feet. Just
All
to
right.
let you know.
Awesome.
What
awesome.
what is that? What is that in feet?
Outreach upload lesson 4.pdf.
I can send it to you.
I mean, you don't want to scroll back for me here.
Which page you want me to scroll back for? You still haven't told me.
I don't know yet because Flatzoid, I haven't seen that, and you won't look at it for me.
Okay, well.
All right. Well, send me the link to it.
Okay. I'm gonna send it to you quickly.
All right. Awesome.
Okay, I've sent it to you.
Oh, it doesn't come up for me. Hold on. Oh, you pasted it twice, I think. There,
Okay.
got it. All right.
Just stop
So
sharing.
now we can all look and we can find where it derived that number from. All right. All right, I gotta change this. All right, and I'll share it so that you can see too. So we can see where that number came from, because these numbers don't just come out of the blue, you know. It comes from somewhere,
Mm-hmm.
right? All right. There we go. So what page was that on you were looking at?
I can't remember. Go down till you find it. But I want you to quickly stop somewhere when you get there. Wait, I think it's the next one. This one. Navigation trigonometry charts. Why would they use that if they don't have trigonometry? That's
Right.
weird.
Well, I mean, they're using trigonometry here to get the distance to the rocket going to the moon.
Weird,
Yeah.
eh? So
Oh.
flat Earth required. Nice.
No, look at the picture. There's a globe right there. Over on the left side.
Drawing a globe.
All right.
I'm sorry. Last time we checked a trigger.
Ju-
It's a
just-
triangle.
just
correct?
just
That's
saying-
a straight line.
Just saying things doesn't change the shape of the Earth. All right, there is that's a nice drawing there. Look at that. Look at the Earth. This first law, people. First law. All right.
There we go.
All right, here is the dip height. It looks like we found the interesting part here. If you look at the picture above, you can see the person looks at the horizon isn't actually looking straight, but down a bit. That's because the Earth is round, not flat. The angle that you look down depends on how tall you are. If you're on top of a building that was in the middle of a big field, you'd have to look down quite a bit to see the horizon. If you're laying on your stomach in the field, you wouldn't have to look down at all. You can see this by looking at the sextant corrections worksheet. It's easier to use a sextant when you're standing, so the angle you're measuring is actually larger than the true angle. This error is called the dip of the sea horizon. Luckily, it's really easy to figure out. Dip equals 1.753 times root h. H is the height of the eye. Yep. So,
notice
we didn't get to the derivation
where's
yet.
R? Where's R?
It's embedded in the 1.753.
Where? Show me.
Well, I'm working on
Show me
it.
where's R.
I'm not there yet. Right. Oh, and this one, it does talk about, look at that, another source of error is refraction, so it does get into that. And so that would be the curved line that comes from the source. All right, now I don't know if it's saying the 1.753 derivation.
Because it's not a derivation of radius, numbskull. It's the ratio of your eyes to the horizon.
Oh, well, that should be something that we should be able to find.
And then we should remind you again that the black swan exists. And then I should remind you again that you even conceded that we have refraction every day, so therefore bent lines, so you can't get an angular reading.
Of course you can get an angle. Of course you can get an angular reading because it's an instantaneous angle. It's not tracing the whole path backwards.
What's an instantaneous angle? Can you bring me a definition up for instantaneous angle?
Tangent. Please? It's tangent.
Where's the tangent?
It's right. It's where they meet.
So if I'm looking at an angle measurement to the star, it's a tangent. McToon?
Hold on. I'm looking for this previous topic before we move on. So all right, there's
You do.
What?
Never mind. Go on.
Okay.
I'm laughing because yeah, you're gonna see now.
What am I gonna see? Does it talk about the derivation of that?
Go on.
Does it talk about the derivation?
No stress, just go on, man.
All right, it looks like it's not derived in here. So you are saying it's some ratio of the eyeball?
Carry on. You're saying it's derived from radius, so show me where the radius in a horizontal line is, please.
It's not the radius in a horizontal line. It's the dip of the horizon. Because like it says here, if you look at the picture above, you can see the person looks at the horizon isn't actually looking straight, but down a bit. This is because of the Earth is round, not flat, right there.
Okay. Let's say my arm is now the horizon. My eyes are above. I'm looking down at my arm, correct?
Yeah.
Is my arm curved now?
No.
So it's height of eye correction because your eyes are above the surface of
yeah,
Earth.
they're above the sphere of the Earth, yes.
Surface of Earth. I don't care if they say it's a globe on there. That's just them having a belief. The fact is that angular measurement requires horizontal and straight lines, which you don't have.
Of course we have straight lines. They're tangents. Again, we covered it before, right here.
No refraction. Eh?
Right here. You see that circle A. The fact that the circle A is curved does not change the fact that the intersection at point C has a straight line ED.
Sorry, is it a tangent to the Earth? Do you take a measurement to?
It's a tangent to a curve.
Sorry.
A tangent to a curve is possible, Flatzoid. This is basic geometry, not a problem at all.
And you are taking an angular measurement from the Earth, correct?
No, from above the Earth, point G on this diagram.
From the above. And then you have to do height of correction to the surface of Earth, correct?
Yeah, yes, yep.
So,
which includes the radius of the Earth in that formula.
To make that surface part of your horizontal, correct?
Nope,
So
it
you have
doesn't.
an
No, it doesn't make it.
elevation angle,
No, it doesn't make it part of the horizontal.
doesn't it?
No, what you're doing
So
is
why
you're
do you
adjusting
need-
you're adjusting for that dip. You need to remove that dip so that you don't have the angular, right? When you're at point C, for example, if you're at point C and you're looking off and say there's a star out at point D, you wouldn't need to include it. But if you're above the surface at point D and to the horizon, you're going to have a different angle because of the elevation above it.
Okay, tell me something. Why, when you use a bubble sextant, you don't require height of eye correction?
Because it's measuring from the zenith.
Horizontal baseline, correct?
Zenith.
Yeah, which is 90 from a horizontal.
Yeah.
The bubble.
It has
bubble
nothing. It
sets
has
the
nothing.
horizontal.
It has nothing to do with the surface at all. You're nowhere near the surface, and that's why
Yes,
they
with a
use
bubble.
it.
Great, great. So it's a horizontal. So what
Again,
happens when you go
what it
to
is,
a nautical?
what you're
and what
looking at
happens-
is line ED.
Why don't you let me finish talking?
Line ED is what
So-
you're looking at. Again,
so
line.
what-
The fact that
so
you
why-
use a horizontal doesn't change the fact that circle A is a circle. We covered this right away. That's why I covered it right away, so that it was
So
clear
again-
that the fact that you're using a straight line doesn't change the fact that the
Sorry,
circle is a circle.
You don't have a straight line to make an angle on your globe, remember? And the fact you do
Why don't I have?
height
Wait,
of
why
eye-
don't I?
And because of refraction, remember?
Yeah, okay, so it adjusts it slightly.
So
And
it's a bent line.
your
So it's a
citation,
bent
I mean,
line.
right here. Look right
So
here.
show
Your
me
citation.
an angle.
Right here.
Show me an angle. Show me an angle that has bent lines, please.
Oh, sure, right there.
No, that's straight lines. I want bent lines.
Yeah, right at point C. Right at point C, you've got
No,
a
that's a
tangent.
tangent.
Yeah,
That's
you've
a
got a
tangent.
tangent
That's
to
a
a curve.
point.
That's how you
That's-
measure an angle. You
That's
take
a
it.
vertex, correct?
You take an angle. You take a tangent at that point. That's what you do. That's what you're doing.
So let's put it this way.
Why,
That
why
point
is this?
C as
Why
a
is
point,
this hard?
That,
Why is
sorry,
this?
so
This
that
isn't.
point
This
C-
isn't actually that challenging, Flatzoid.
can you let me talk? So that point C is a 180-degree straight horizontal line, correct?
All right, I'll draw a little something for you to help.
Is
Help you
that point
understand.
C? Is that point C a straight 180-degree line, McToon?
It's a straight line. There's no degrees
So
that are. It's in a
yeah,
straight-
that's a 180 degrees because that point C is a point. So in other words, it's a vertex. So it's 180 degrees because a straight line with a vertex in the middle is 180
All right,
degrees.
let me show you this right here. Here,
That
see
means you wait. You
It's
know
right
that
here,
means
right here.
horizontal.
No, it doesn't.
You know that means
so look at
flat.
this. Look at this. No, it doesn't. Look at this right
Yes,
here.
It does.
This is a point right there in space, not touching anything.
I can't
And
see
here's
it
a
very- you're
here's
very-
a curve.
You're very small. We can't see anything. You're very small.
All right, I'll stop sharing. So
Might
you
have
can
to
see
stop
it.
sharing. Yeah.
All right. So here we go. Here we've got this curved line going all the way around, and we've got this point off in space here, and right at this point here, and at this point here, we've got tangents, and so we can measure that angle right there. We can
From?
measure that angle.
Okay. Is
So
that
now-
angle from or to? Is that angle from or to? McToon?
Both from and to. Now we can do the same thing.
No.
We can do the
No,
same
a
thing
tangent,
here.
a
Watch
tangent
this.
Is two.
This
A
is-
tangent is
This is
a point.
amazing. This is amazing. You're gonna love this. All right, now look at that. We got this gull wing here. See that? At that gull wing, you can measure. You can measure angles. And the fact that you can measure angles does not change the fact that the lines coming into that point are curved. You see that? So you measure the angle between those right there. Not hard to do.
Sorry.
There you go.
when
That's
last
how you
is
measure
the-
angles. That's how.
when
So
last-
so when you're talking about refraction, you've got a curved line coming in, and at that instant, I said instantaneous before. That's what I'm talking about. Right at the point there, this curved line comes in, and right at that point, you're measuring that angle. And so back to the citation. I'll share it again so that you can see your citation. Right. I'll share it out to you again.
I was gonna draw something for you too. Oh wow, this is so funny.
All right, so back to your
Okay,
citation.
right, yeah.
It says another source of error is the refraction effect in the atmosphere. The atmosphere of the Earth bends the light coming from the sun. The sun might be below the horizon, but the atmosphere will bend the sunlight so that you still see it. Just like the dip, this makes the altitude seem larger than it actually is. The amount of bending depends on the atmospheric pressure, the temperature, and your altitude. A good approximation for this error is, and then it gives this formula there. And it gives us, P is the pressure.
The triangle. Ooh, the triangle is
Where?
called the delta and the minutes of arc.
What? What triangle?
It says there, the triangle on screen.
Uh-huh.
So it's using a triangle.
No, it's called, it's delta. It's the Greek letter delta.
Yeah.
It's giving for people that don't understand the Greek letter delta, like apparently you don't.
I know what delta
It's just saying delta. It's saying this little triangle here is the Greek letter delta.
Yes, it does. But what is delta in the specific reason?
The difference in angle because of the refraction.
So straight lines then.
Oh my
and you're
gosh.
claiming to
Oh my gosh.
The difference in angle is straight lines.
How
is
is
it not?
this so hard? Oh my gosh. No, the difference in angle is an angle. It's still an angle.
You require straight lines to have that angular reading, McToon.
Yeah, tangent at a point. Oh my
And
gosh.
by the way, I also got another question for you.
Javardo, you nailed it. Hold on, I gotta scroll back to see what Javardo said.
No, I want to ask you a question.
Hold on.
So answer me something. Refraction. Does that correction come after you've taken your angular reading or before?
Of course, you can't do it before. Yeah, he says it called this.
So you measure.
I predicted. Watch this. Javardo says I predicted that he was going to say the delta stuff. Absolutely. Just because it's the shape of a triangle, he thinks that there's a triangle there. There's no triangle.
No, I was
delta
pointing
means a change. That's why they use it the Greek letter. It's hilarious. I love it.
You see, this is why I call this guy dishonest. I was trying to point out, as in delta, the triangle, as in
it's not a triangle.
Steps triangle.
No, it's no triangle involved. There's no triangle. It's just the Greek letter delta.
Yes.
Oh my gosh.
What's delta?
It's a change in something. That's what delta means in math.
Change in angle. Context.
Change in angle.
In this context, change in angle, straight lines.
No, change in angle, not change in line. Change in angle.
Angle is a line.
No, it's not. No, it's not. An angle is an angle.
It's a separation. It's a separation between two straight lines.
Yes, tangent at a point. I got it right here. Same thing right there. Tangent at a point.
Sorry, does that look like Earth to you?
No, I'm just giving you a little geometry lesson, Flatzoid here. No, you can take an angle that's tangent to a point. Oh my gosh.
The guy that says to me you can have bent rays being straight.
No.
He's trying to
the rays are bent, but at that point you can use the tangent.
So again, you do the angular measurement first, which is straight lines.
Yeah, right there. Yep.
Requires straight lines.
And then you apply the formula. Correct. And then you apply the formula on screen.
Correct. Then you correct for bent.
Yeah.
Correct?
Yeah, of course.
So you can't get an angular reading if it's bent, McToon.
Of course you can.
You can't get an angular reading if it's bent, McToon.
Right there, theta. The theta, that's an angular reading right there. Not hard at all. This isn't a challenge at all. I mean, it's not calculus even. I mean, you can do this mathematically through calculus, but I mean, I just do this draw, and then you can actually just put a protractor on here and measure that angle.
Protractor using straight lines.
Yeah, at that point, there's a tangent at that point. The fact, and again, that's why I brought this diagram up at the beginning. The fact that there is a line ED that is straight does not change the fact that circle A is a circle. ED is tangent at point C. You can measure an angle to line ED. That does not change that the circle is a circle.
Do you mind me quickly sharing my screen again?
Oh, do. I will. This is great. Okay, go ahead.
I can't believe this guy. Anyway, what's this? This would be your sphere, okay? For instance. Now we're going to take an angular reading. Well, first we have to have a zenith. You agree with that? Correct?
Yeah, go ahead. Zenith? That's a nice zenith.
This would be a 90. Okay. Now we need
It's-
to have our
Actually, I like using zenith as 0. Let's do that.
whatever.
I
Okay.
find it
Well, we
easier.
have we got now your horizon. This would be a sensible horizon where you're standing and looking out.
Okay.
Got that?
Okay.
We got a problem for you already, by the way. Okay. We got the star here. And I'm going to take a angular reading to the star.
Okay.
So this would be the one line, and this would be the second line, correct?
No.
So this will be an angular reading.
No. You can't measure to that because that's not what you see. Can you move the circle down a little
Sorry?
bit? Can you move the circle down or the oval? Can you move that a little bit, or is it stuck? Is it an object, or can you move it?
It's supposed to be the earth you're standing on, according
Yeah,
to you.
but you're a little bit above it. Can you? So I know it's out of scale.
It doesn't matter. It doesn't matter.
Can
You're
you move
saying we're
the?
on a
But
ship.
can you
We're on
move
a
the
ship.
oval? Oh yeah. So then you're gonna have to measure down to 3. You got to draw a third line that's below
No, that's
2.
that's still gonna come. Now,
But
what
how did you
happens-
measure? How did you measure to angle 2? Because you can't see that. All you can see is 3,
That's
which you
your
didn't draw
horizontal
it.
baseline. 2 is your horizontal baseline.
But you don't. But
your
that's not what you see.
angular-
Yeah, but that's not what you see. You don't see it.
Sorry, 3 comes afterwards with correction. You know, when you do height of eye correction, that's where 3 comes into account.
Okay,
correct?
let's see it. Let's see
so
it. This is gonna be good.
now we've done a reading, correct, with 2 straight lines to the star.
No,
No, so that's not
you
an
have
angular
one.
reading.
You have one curved line to the star and one
Where's
curved
the
line
curved
to the
line?
horizon.
Show
That'd
me
be-
the curved line.
That'd be
Jeff, please.
that'd be line number 1 is slightly curved.
But what's an angle, McToon?
Yeah, at a point, it's an angle between 2 lines at a point. But that doesn't mean that
So
the path of light
here's
had
the
to be
only
straight.
point.
But that,
Here's
that
the-
does
here's
not
the- here's the
that
only
does
point.
not mean that the path of the light had to be straight in order to get there to measure the angle.
Oh yes, an angle is 2 straight lines. So here's
Yeah,
your vertex.
but it does not mean.
Here's your point.
But
Here's
let
your
me
point.
say it
This is
again.
C. This is, remember, this is C that you put there.
It
Now, tell me, how did I get this angular reading from C? So it's from the Earth to
Yeah.
the star,
Okay.
correct? According to you.
it's at a point. You're just at a point C. It doesn't matter where the point is.
That's the vertex because
Yeah,
here's
yep,
the
that's
one
correct.
line, the second line.
Correct. That's a vertex. Good job. But it doesn't matter where it is. It doesn't have to be on the surface of the Earth. It could be anywhere above the surface, in fact.
I agree.
Okay.
Because your sensible horizon is your horizontal reference plane. Correct. You get that? Now,
Yeah,
notice
yeah. What you're talking about is it's tangent at that point, right?
okay. So now we measured our angle. We're gonna just say 50 again. It's not to scale, obviously,
Okay.
guys.
Okay.
Oh, sorry. Say 50 at 90. And what does that make internally? 40.
Okay.
Correct?
Okay.
So that means that to have our 90, it will just have the same 40 and it would have 50.
Okay.
Because it just corrects it. Okay. Now, what do we have in common here with these angles?
They're all degrees. They're all in degrees. None of them are in radians. They're all multiples of 10.
Right.
They all use the same font.
Great. Okay. So you would agree that all the degree measurements, degrees, come from the straight line measurements.
No, not necessarily. Yeah, the path that the light got there, the path that the light got to your eye does not have to be straight.
Why? What's an angular reading again?
It's instantaneous, like I said, just at that point, but it doesn't mean that it has no bearing on the
Sorry,
path that the light took.
The only tangent here is you on the ship on the surface of Earth, correct?
Well, it's not something you see, of course.
So that's the only tangent then. And what is the other?
No,
half of the
there's another
tangent? What's the half of a
Oh,
tangent?
hold on,
Would
there's
it be a straight line?
well, the half of a tangent is just tan, or the last half would be gent, or actually the G gets split in half, so it'd be like tang, and then gent.
Let's
Like, but I
let's
can't
let's
only half pronounce G. I can only wholly pronounce G. So it makes like G's got to get borrowed, kind of like a valence electron, you know. So
okay,
can I call it
let's put
tang?
this way.
Hold on, half of a tangent is tang, and the other half of the tangent is gent. How about that?
Great. Okay, so we got
Okay.
a single tangent, aka us on the boat, on the ship, on the ocean, correct? And what is a tangent? It's a straight line touching at a point
At that point,
on a
yes,
curve. Okay, great.
absolutely. At that
So
point, yeah. But now I want to be clear. There's two. I just want to say. Hold on. Can I back up just one thing? There are two tangents to curves at this point here. Just I'll come back to that if you need.
So that straight line is the other arm for the angular reading of the star, correct?
The other arm?
Yes.
There's
arm one and arm two.
There's no arms. What are you talking about? Arms?
An angle is two arms, two straight rays.
Two lines? You mean? Else, how about
Arm
lines?
one.
We don't need to.
Hypotenuse.
We don't need to.
hypotenuse.
Yeah, but we don't need to anthropomorphize these angles, right?
No, it sounds to me like you're trying to run away from an angle here.
No, I'm just saying that why are you using the word arm?
Because it's trying to make it to understand it's like two straight arms, not curved arms.
Lines. How about let's just use the word lines? But
Right,
lines is a great word. Yes.
Okay, so that straight line going to the star cannot give an angular reading if it was bent.
Wrong.
Correct?
You can give an angular reading even if it was bent.
Okay, so the tangent, can the tangent be a curved line?
The tangent is a straight line to a curved surface.
So
yeah, it's tangent at a point on the curve. That's how a tangent works.
So if your tangent line is your horizontal baseline, which is straight, correct?
At that point, yeah, at point C.
And your so-called elevation angle would be curved. How do you get
both are curved?
Angular reading.
Both 1 and 2 are curved. Yeah, both 1 and 2 are curved.
How? You just contradicted yourself. You said tangents are straight.
Oh yeah. Sorry. So, well, because you didn't draw the actual measurement here, right? You're drawing this hypothetical thing that you don't actually ever see, and that we measure the angle from 1 to 3, which you didn't want to draw yet, but you measure the angle from 1 to 3, and then you do the dip correction and refraction correction to get as close as you can to angle 2.
You measure the angle from 1 to 2 and you correct for 3.
No, actually you don't, because you don't see 2. That's why I wanted you to draw number 3 so that you could actually, so we could talk about what you're measuring 2.
Sorry, you do know what a sensible horizon is again, correct?
Geez, yeah. All you can see is your visible horizon. That's all that your vision can get.
That's all you see, the visible horizon. Okay.
Yeah.
So now we're going to go to 3. So let's
draw 3 for us, please.
Okay.
No, it's not that. Oh no, you can't. You can't. It's got to be just below. No, hold on. No, way up. Just below number 2. A little higher, even if you can. A little higher if you can. Yeah, there you go. That's good. That's good.
Okay. Now I've got a question for you. The GP of the star. Where would the GP of the star be?
Can you take? Yeah. Oh, hold on. Put that line back.
I'm trying to.
Right there. Okay.
Sorry. Okay.
Are you able to grab line 1 there and copy it?
No, this is paint. But anyway,
I don't use paint.
GP of the star would be like this, correct?
No. The line from the star would not actually be on the screen. It's off screen. That's what you need to do.
So the GP of the star would be here, correct?
No. So can you do this to fix it? Get the star off the screen and just have that line 1 go off the edge of the screen. And then just
this black one must go down all the way.
No, that one actually should not be there at all either.
Oh, that one should go all the way.
There you go. Continue. Yep. And get the star off of there and get that line from the star to the ellipsoid there, or the ellipse off.
And then you want this one to go like that, correct?
It needs to be parallel to line 1.
So
But
two
but
straight lines,
but the
correct?
problem is it needs to be moved down a little bit because it's not
So
quite tangent that or 90 at that point.
it
Can you
doesn't
move it
matter,
down?
but we're making a
Okay.
point.
All
So
right. So
the
for correctness now, let's get rid of that line from the star to the surface.
but that's what you're measuring.
No, no,
I'm
that one
doing.
right there. Yeah, get rid of that one. Delete that.
Okay.
There you go. Okay. So now what you're measuring then is from 1 to 3. That's what you actually measure because that's all you can see. Right? And of course you don't have your label for 3, but that's fine. We know where that is. No, they get the star out of there. The star's off screen.
I'm gonna put 3 on. No, the star. No, the star
This,
can't be off screen. You can see it.
yeah, but it's so far away. It's much farther away than
No. This is the GP
dude,
of the star.
that
Here's the GP of the star.
that 3 looks drunk. Too much
It
tune
doesn't
shine.
matter.
Flatzoid,
This
how
is the
much tune shine have you had today?
Not enough. This is the GP of the star.
I don't know.
correct?
That 3 tends to disagree.
Sorry, is this the GP of the star, Neptune?
That would be the GP of the star. Yeah.
Okay, now, indulge me this. Then, if that's the GP of the star and you can't see through a curve,
Yeah.
hmm,
Yeah, you're
this
no. Why do you put that back up? That's not what we're doing.
because because we
You
completed
seem
a
a little
triangle.
no, there's no triangles involved.
Yes, there is. I
No.
brought up
No, there's not.
I
There's
brought up, I
no.
think 6 or 7.
But you didn't
6 or
show.
7.
But your
I
one
brought up
citation. But Flatzoid, your one citation didn't show this to be the case. Your
I
one
brought up 6 or
citation.
7.
Yeah, but I asked you to bring up the one where we could look at how triangles are used, and you didn't actually show it. I mean, I can.
I even sent
Flatzoid.
it to you. You went through it and you showed triangles, Sakatoa.
No, it
Sakatoa
didn't
is a
show the process.
Triangle trigonomic function, is it not?
Flatzoid. It didn't show using it in celestial navigation, buddy.
Okay.
It didn't show it. It didn't show it.
What's this table? What's this navigation trigonometric tables?
I don't know. Is that on the same page that you sent me?
Yes.
All right, hold on, let me find it. Navigation trigonometry table. Yeah, that's just giving, in case somebody doesn't have a calculator handy. But where in the process of celestial navigation?
Do they use this for the trigonomic function?
I don't see where in the process that they're using trigonometry to do. In fact, this page that you give me doesn't actually do any celestial navigation. It doesn't show how to take angles to a star and convert them to a location. Did you not notice that?
Did you not notice I already showed you how?
No, it's not in there anywhere. What page is it on where it shows that you take the angles to a star and convert them to a location?
That's how celestial navigation
What?
works.
Show me
19.
which page. It's a 33-page. Haha! Are you a Freemason? 33-page PDF here. Which page shows how the celestial navigation is done using these triangles? Which page? I'll jump to it.
Let's look.
I put it in the chat for everybody here to look at, so they can also help you find the page.
Yeah, please help us look.
Yeah, help him find the page. He's desperate to find the page.
Help us look while it's showing us using Sakatoa, which he says would not be used.
Which page? Which page?
Use it.
But it's just which page is using it. Which page? Show me which page is using it to do celestial navigation.
Tell me why they would explain.
Hold on, you're changing the topic. You're changing the topic.
No.
Which page? Which page shows it?
Why would they show using it if you don't use it, Neptune?
Just waiting. You're not showing. It's
sorry.
not there.
Aha. Okay. Optional determine latitude. Write down the exact GMT Greenwich Mean Time. Obviously, this gives you the information you need to find your latitude and longitude. Knowing that the measurement was taken from the sun at the highest point of time, there was noon. This is the angle of the sun of the horizon. Can you tell the latitude? If you also did step 7, you could determine the longitude, knowing the GMT time and time where your tells the difference between the location of Greenwich, England, 0 degrees longitude, and your related time difference, the distance, and find your longitude. The actual compute your latitude and longitude, you need to do a number of long calculations. Either way, the computers can help. Lessons for collaborating. Geometry, the mathematical. Trigonometry. These are the steps they want you to actually do.
Okay, what page you on?
6.
Okay.
Hmm.
All right. Where is it? Let's see it.
Read it out.
You didn't actually read out anywhere that it was applying triangles to celestial navigation, Flatzoid.
Sorry, what does trigonometry and triangles mean?
I no, you didn't actually show where it was doing it. The part
Less. What does lesson vocabulary list mean?
it's just a vocabulary list. It's not the step-by-step instructions. Oh my goodness, Flatzoid.
So what does it mean?
What does the vocabulary lesson mean? A vocabulary is like a small portion of a dictionary that tells you the key topics in that section. That
I know
that
you're
yeah, so you
dumb,
can give you
Matthew. I know you. I
the
know you're dumb
definition
and you
for
got hard.
specific words. So
I know you're dumb
where
and you got a hard time reading what lesson vocabulary
oh my
list
goodness.
means.
I'm still waiting for
means- that means
Flatzoid.
this-
The reason
that
what we're
means-
going at here is we're finding the
That
page in
means-
this that uses trigonometry to do celestial navigation, and you haven't yet shown me which page. Which page?
They just told you how to do it.
Which page?
There we go. Another page. 11.
Page 11. All right, so 11. We're going to take the angles to stars.
There we
Right.
go.
This is just trigonometry review. There's no star angles in here anywhere. Nowhere in
No
that does it
triangles.
say.
Wait,
Nowhere
would
is
be
it.
the
Oh my
star.
gosh.
would B
Where?
not be the
Well,
star?
show me the page where it says B is the star. Go ahead.
Wow.
Show me the
Talk
page where
about
it says B is the
dishonesty,
star.
guys.
Yeah, exactly.
Talk about
Where?
dishonesty.
Because nowhere on that page does it say that B is the star. That's
They're
dishonesty.
explaining the trigonometry
Oh my
to
gosh.
the students.
Come on. Where?
Correct?
What page shows the triangles in celestial navigation? What page?
I got a triangle.
We
on
haven't
screen
there.
now.
I mean, I have. It's a trigonometry review. So I put in the live chat again, everybody. If you can help Flatzoid, he's desperate here to find the actual angle, the triangle that's being applied in celestial navigation, because I don't have any. I don't see anywhere. I mean, you can jump down here. Jump down to page 12. Question 7. Task 7. It's a
Sorry, what does number 3 say that I got on here?
It says have students use calculators or trig table test to do the rocket to the moon problem.
Trick table sheets, correct?
Yeah, the rocket to the moon problem. That's not going to work out well for you.
No, it works out fine for me because it's making my point. They're using a triangle. They use trigonometry to do what they need to do.
Oh my gosh.
Oh, really? It's weird how this guy says there's
first
no
law.
triangles.
I mean, this.
Yeah, first
Jump
law
down to
of
page.
Neptune.
Jump down to page 30. 16, and you'll see the rocket ship to the moon. It has
Oh, yeah, I got it
the
here.
distance to
Got
the
it here.
moon, 382,700 kilometers.
Mhm.
First law.
Sorry, is this making a triangle for the rocket ship to the moon?
Yeah. The moon is then 382,700 kilometers away.
According to the narrative, yes, but that doesn't make it true. So, tell me again, is that a triangle? On the page, you said they're not using triangles, McQueen.
This isn't celestial navigation. That's not getting the observer's location, Flatzoid. This is getting the
Have you never
rockets.
done? Have you never? Well, you know you can do the same with this for celestial.
Oh, show me
navigation.
the
Have you never-
show it to me.
Have
Show
you
it to
never?
me.
You know you can do celestial navigation to the moon using the moon and
All
the
right,
sun as
all right,
well,
let's-
just like the stars. McQueen.
All right, let's look at this. We've got page. Oh my gosh, Flatzoid. You should have read this first. Dude, you don't... Why? Flatzoid, why? Why didn't you read this first? You're killing yourself.
What do you mean I didn't read this first? This is making my point, and
No,
you're
it's not.
laughing like a
Nowhere,
crazy lunatic.
nowhere
because
in
you-
here is it showing how celestial navigation uses triangles. Oh my gosh. Dude, I love you,
Screen
man.
again.
Yeah, I love you, man. This is ridiculous. I mean,
No,
you're
this is ridiculous. It's amazing how this guy doesn't. He says,
I like that the invisible island problem. Again, this is all horizontal stuff. That's pretty good. What page you on there?
Horizontal.
Yep.
It's horizontal. Tell
Yeah,
me,
yeah. You
what-
can measure horizontal
how do
angles
you-
and vertical angles, both. Amazing.
So when you do a horizontal angle measurement, McToon,
Uh-huh.
you require that to be horizontal, not curving.
It's just the horizontal component of an angular measurement, right? Every angular measurement has a vertical component and a horizontal component. So you're just isolating the horizontal component. That's all it's doing. Again,
So
again,
horizontal doesn't curve then.
just like I said before, the fact that you're using a straight line in Euclid's Book 3, Proposition 18 does not change the fact that there's a circle involved. It doesn't make that circle not be a circle anymore. It's still a circle. All right. Hey, could you do this one more time? People are like, hey, do this. So jump to page. Hold on, let me.
Yeah, you can share the screen.
All right. Dude, and then we need. I got some super chats. I hope you got some super chats.
I also
too.
got super chats as well. Yeah.
All right. We should do that next. So all right. One more time. I just like this was pretty good. Are you seeing it? Oh, I need to change this. There it is. Where'd it go? There it is. All right. I just want to show that one more time. All right, what do you got for super chats, Flats? I just poking at. I'm just poking at you, man. All right.
Just want to get something quickly.
Hold on. Somebody had something. I think I'm going to read this right away here because I think you're going to like it. The grumpy old mechanic says, I will pay Flatzoid $500 to go to his local university library and read the abstracts of 20 papers, each from the Journal of Astronomy and Astrophysics and the Journal of Geophysical Research. He must live stream it. So there you go, $500.
$500, I'll do that.
To live stream reading the abstracts from 20 papers.
Okay.
There he is.
I'll do that for $500.
Grumpy old mechanic. Contact Flatzoid. How can he contact you?
Flatzoid@gmail.com.
There it is. All right.
Okay. Let me go to my super chat first quickly. We can do 1-1.
All right.
Let's see. Okay, from Duncan McLeod. I love this one. He says, the top, please ask Mattoon, the top line of the angle goes from the observer to the star, and the bottom line of the angle goes from the observer to where exactly?
The edge of the visible horizon. Just like in my...
False. It goes to the GP of the star.
No, it doesn't. No, it doesn't.
I can show you on...
No. Here, I'll demonstrate. Here you go. I've got it.
You know what a line of sight is?
There you go. All right, so there is my...
It's not a nautical sextant.
There you go. It doesn't need to be a sextant, and any angle measuring device works.
Sorry, when we talk about nautical navigation, celestial navigation, we're using nautical sextants.
I've used this very same phone to obtain my position by measuring angles to stars, so it works just fine. So, but whether you're sighting through a phone or through a sextant, this particular angle right here is going to be the same. It doesn't change. So that's not the GP. If you remember later, I showed the... I'll bring it up to right there, right up that to the tip of that the rocket there. So the tip of that rocket to the GP of the ball is not the edge of that. That's not what you're measuring. Now, since I can do celestial navigation and you can't, I kind of know what I'm talking about. So, all right.
Okay. Can I share my screen quickly?
Yeah, go ahead.
2 seconds. Okay. The point where the line crosses the surface of the Earth, we call the geographical position of the star, or GP. And observers positioned in the GP of the star will see it directly in the vertical, above the head.
Yeah. So if they're right underneath it, they look straight up, they'll see it. So what?
Okay. Now I want to show you something quickly. When you go and look at the star, is it on the same azimuthal plane as the observer?
I mean, you could the same azimuthal plane? No. No.
It's not the same plane. Is that what you're telling me?
No.
So that's not the same azimuthal plane. There's the observer. There's the star.
Yeah.
There's the GP of the star.
Wait,
Same plane, correct?
where's the GP of the star?
On there,
On
at
on
that point.
that curved line H? Why do you have a
No.
curved line?
That's the celestial sphere. Remember when you talked about
Okay. Yeah, but
celestial
you
sphere,
don't like those
which is
curved lines.
optical?
How did you get that curved line?
Why are you obfuscating from the point that it's on the same plane?
It's not at the same plane. Flatzoid. It's not. It's not the same horizontal plane, right? Of course, any 3 points you can define a plane. All you need is 3 points. So you can always define a plane to include any 2 arbitrary points. Just pick a third.
Great. So the point he's making is, if you're standing on your surface and you are, let's say, your sensible horizon is your point, you are looking out to the star, which would be on the same plane as you
No,
to get that measurement.
no, it's not on the same
Yes,
plane.
that's what does line of sight mean?
It's just a line. It's not a plane. A line is a line, not a plane. There you go. There's a good diagram. You see that body there? The GP. Now that in that diagram, it doesn't have somebody showing at an higher elevation, but you see that geoidal horizon is what it's calling. That geoidal horizon that you would be viewing is not to the GP. So, thank you for that.
It's on the same plane,
No, it's
correct?
not. No, it's not. It's a separate plane. They're
No, it's
not
definitely on the same
coplanar.
plane.
They're not coplanar. Your diagram shows that they're not.
Okay,
Super.
so let's move on to the circle of equal altitude then.
Is that
Tell me
a
again-
hold on, is that the next super chat?
No.
Oh,
Same
okay.
thing. So circle of equal altitude, would that be the same plane?
No.
Circle of equal
So
altitude, not
what-
the same plane.
Same plane as what? What are you talking about?
Observer to celestial star, correct? You'd be
Okay.
somewhere on this circle to the celestial GP of the star, correct?
Okay. So yeah, I'll explain
So
it.
if
I'll explain it. You
the
ready?
same plane.
Hold on, let
same
me
plane.
I'll explain it if you let me.
Go ahead.
Okay, so you take a sphere and you take the GP, which the GP is a point from the origin of the sphere to a point on the surface out to a point on a concentric sphere farther out, an undefined distance away. And that defines a line. So at that line, you take at a elevation, a radius that's less than the radius of the sphere, and you have a plane intersect that line orthogonal at that point. And then where that plane intersects the sphere is where you're going to have your circle of equal altitude. And of course, the altitude is it's a little bit of a misnomer. It's not an altitude in linear units. It's an angular elevation, angular altitude.
So plane. If it's on the same plane, then
Yeah,
as you said,
the plane is where the plane intersects the globe.
So the plane circumference of circle equal altitude where you're standing, the GP of the star is on the same plane.
No, the
as
GP is not on the same plane. The GP is on a
you just
different
said
plane.
it is. You just said it's on the
No,
same plane.
no, I didn't. I said all the entire circle at where the circle intersects the globe is on the same plane, but the GP is in the center of that, and it is not on the same plane.
It is on the same plane.
But no, go back
Showing on
scroll back,
showing-
go back to your diagram. Right there. There you see the GP is at a different location than where that circle intersects.
I don't know why I have to do this.
It is a little more complex geometry, probably high school level.
Yeah, this is very simple stuff, mate. Circle of equal altitude. There we go.
Okay, yeah, you have a simplified diagram. Okay, go to the
Okay.
one. Go to left and down,
no.
left and down from the one you
This is gonna be
selected.
better.
No, left
Okay.
and down. Hold
Let-
on, left.
I think I like this
all
one,
right,
so
all
you
right.
can read what's on screen, maybe. Assuming your position circle of equal altitude, intercept. Yeah, the interceptor method. Okay, Okay, let's go to where it shows site reduction. There we go. The analogy of observing a flagpole is often used to describe the circle of equal altitude principle. An observer who sees the flagpole at a certain altitude will be on the circle with an equal distance around the pole.
Yes.
If another observer sees the top of the flagpole at a high altitude, then he is on a circle that is closer to the flagpole.
Yeah.
Another observer sees the top left of the pole, lower altitude circle
Yeah.
must be further from the pole.
Okay.
You get it? On the same plane.
Yeah, that circle is on a plane, but on a curved surface like the Earth, that's a different. The point that is the GP is not coplanar.
Sorry.
All right, go to the next slide
we
here.
Literally
All right,
seeing.
hey,
We
jump
literally,
jump to the next slide.
Let me first finish.
Hey,
So
jump to the
we
next slide. Go
got-
ahead.
So we
This-
got
I mean,
site.
we're getting bogged down in super chats here, but just jump to the next slide. There you go. There's a good diagram.
Homoto, yeah.
Excellent diagram
Homoto,
there.
yeah. And you can do homoto showing flat. So because they draw it over a curve, so therefore curved, you say. But let's go back to what the triangle
Oh,
show
you
on the
didn't
circle.
you didn't like that, huh?
No, because it's just you guys don't understand.
Oh, that's a nice one. Very nice.
That's a nice one. So same plane then.
That circle is on a plane. It's a different plane. It's not coplanar with the GP though.
Oh, so he's not measuring a distance, got a calculated distance of, let's say, 3,000 nautical miles on the same azimuthal plane.
No, not on the same plane.
So what is line of sight then? Because this
Yeah.
is sight reduction.
Yeah, it's not line of sight.
Yes, it is. It's called sight reduction.
Just
for a
because it's
reason.
sight reduction doesn't mean it's line of sight. It's not line of sight reduction. It's sight reduction.
Circle of equal altitude on the Earth. Okay. This
There you go.
radius of the circle of equal altitude distance to the GP is equal to the zenith distance.
Yeah, yeah.
I don't know how much more plain I can make this.
Yep, yep. Draw those on a flat surface and make them intersect in any reasonable way. You won't. $10,000 is still waiting for you. The first one to do it. It's funny that you said that it's possible, but Flatzoid, nobody has yet done it. How come you haven't done it?
Why haven't I done it? Because it's not really a challenge. We already went through it on a live stream showing that it's just literally.
But Flatzoid, what you said, you claimed early on in our conversation here that celestial navigation using only flat Earth is possible.
It is.
And you have not
It is
ever
on it.
shown it happen. Why
Again,
haven't you? Why haven't you done it?
It is flat Earth. You even said.
Why haven't you done it?
don't- You conceded you needed two straight lines to have an angle. You conceded we needed triangles.
I did not concede triangles. Nowhere in celestial navigation
Oh, wait,
are
you
triangles
didn't
used. Nowhere in
Well-
celestial navigation do we use triangles. You did not show any application of triangles in celestial navigation.
While I brought it up on screen with many.
No, you didn't. You didn't. You just said, "Oh, look, they're talking about triangles." You didn't say, "Here is the process that uses triangles in celestial navigation." You never did that, Flatzoid. It wasn't in your citation.
I brought up more than one citation saying they use trigonometry.
And I asked you for all of them,
Triangle.
show where they do that process, and you did not. Your one citation that you chose to show did not show what you thought that it was going to show.
Explaining it doesn't mean it's not the process, mate.
Well, you just need to show the process. You did not show the process.
I did. But
Never
show it
did.
again.
Never did you show the process of
Okay,
using a
okay,
triangle
I'm
to get the
I'm gonna
actual
say-
position. You never
Okay,
did that.
I'm gonna do it. I'm gonna do it again, just for you, McToon, because this has been done many times. Let's see if I can quickly share screen. Shown, and by the way, we can't go on too long. It's kind of late here. I'm gonna do this again for you, okay? Because this has been done for you many times now. It's not hard to understand. Let's take a line. This would be the surface of the Earth, or whatever you just want to have. Doesn't really matter. Can just be a normal standing on a boat. We got our zenith, which is a 90. We got a star, which is there. We're going to have an angular measurement. Remember, 2 straight lines. There's our 2 straight lines.
Okay.
We're going to close off the angle.
Okay.
This would be 90 minus whatever we measured.
Okay.
Let's say we measured 30. Okay. It's going to give us 60. 60 times 60 gives us our distance in nautical miles.
But you
So
never
that will give us,
but you used the
that gives us this
radius.
distance.
Sorry, you used the circumference of the globe in that though, Flatzoid. That's
What
the problem.
circumference? I can use any circumference.
21,600.
Show me where I use circumference.
That's 60 nautical miles is a portion of 21,600, which is the circumference, the measured circumference of the globe. Flatzoid.
No.
You use
it's
the globe
the-
in that. Flatzoid.
No.
You use
no,
the globe.
Sorry.
All you've done is show that you have to use the globe
sorry,
to do
did-
it.
Sorry, did I read a measurement over this
Oh my gosh.
index
All-
arm
You're
reading?
gonna need R for that. Flatzoid.
Sorry,
Dude,
sorry.
you keep using the globe. Why are you using the globe when you're trying to use flat Earth? You're just shooting yourself in the
holding-
foot with a big Dylan minigun. Just over and over and over. You're shooting yourself in the foot.
Can I
Why? Why? Oh,
Is this
go
too, is
go
this
ahead,
too
go-
hard for you? Is this,
go
is
ahead.
this too hard for you?
Go ahead.
You already conceded that these are degree angle measurements.
Yeah,
over
angles.
this
It's no
arm.
concession that they're angle measurements. It's not a problem.
Oh, so if it says 20 degrees, that's not an angular measurement.
No, it is an angular measurement. My goodness, why are you going off on this weird thing?
Great. So the sextant, aka 60 degree, is a segment of a circle. We're measuring the celestial sphere, correct?
No, we're not measuring the celestial sphere.
Yes, we are.
Incorrect.
The star is in the celestial sphere, correct?
The star is, yes, but we're not measuring any linear
So
distances
when
within
I
the
take
celestial
a-
sphere.
So when I take angular measurement to a star in the celestial sphere,
Yeah, it's just an angular
am
measurement.
am I measuring the floor or am I measuring the angle to the star in the
Just
celestial
the
sphere?
all you're measuring is the angle
To the star in the celestial sphere, correct? So not the floor.
to the well, of course the horizon is involved in that. So you've got the surface of the globe as part of it, and the location of the star
Now
in the
surf-
celestial
now the
sphere is part of
surface-
it.
Wait. You guys been telling us the surface of the globe has nothing to do with it. Now it does.
Why would I say that? I've never said
Because
that.
you got
Where
you
did
guys
that
do
come
say
from? That came out of the blue.
great. So we do use the horizon then for horizontal.
No, we use the horizon, but the horizon is not horizontal. The horizon is not tangent to the point. It's always a dip. We already covered that. There's a dip.
So now you have to now you're contradicting yourself again. So we got straight
No,
lines.
oh no. I've always used the same thing. I mean, I
So
like
we
I
don't
said,
have straight lines.
I've
We don't
gone
have
through
straight
this
lines.
book. I can do celestial navigation. I know how it works. If you give me star angle measurements, I will use the globe and tell you the location of the observer. If I give you star angle measurements, you will never give me the location of the observer. I know
Okay,
that.
nice obfuscation.
It's not an
So,
obfuscation. That is 100% confirmation that the Earth is a globe. Unchallenged.
Okay.
Unchallenged
yeah.
confirmation.
And now you
That's
won't
what
let
it
me talk.
is.
Now you won't let me talk.
You
So,
can't challenge it.
So let's make this clear. 2 straight lines give you an angular measurement to a star in the sky using a instrument that requires parallel light rays
No,
to work in succession
no.
with a inclometer, I mean with an index arm reading of an angle which in degrees
They're just angles.
gives
Yep.
you
Why do you need to
lets
keep
you
going over this? All
calculate-
that a sextant does is measure angles.
calculates
We agree.
which calculates your distance
No,
to the GP of the star with
no.
a circle of
There's no.
based on your line of sight with straight lines.
No. That's not how it works.
Wow.
That's not how it
That's
actually works.
Exactly how it works.
It just measures angles. Everything else is the process you apply after you measure the angle.
You can't measure an angle if you've got bent lines.
Of
Mr.
course you can. It's easy.
You can't measure an angle if you've got
It's
bent lines.
easy. Let me
Angles are straight
let me
lines,
tell you
Maxine.
this. let's say you're watching Smokey and the Bandit. Have you seen that movie?
Yes.
Okay. Let's say that the bandit in his Trans Am is driving along and he's taking a whole bunch of turns on that road. And when you're standing there at the finish line, right? Right? At the fair where they're going to deliver the beer. And can you measure the angle that between, the stadium stand and the Trans Am as the Trans Am heads towards you, even though the path that it took from Texarkana all the way to you was not a straight line? Can you measure that angle when it gets there?
Sorry, it's a false equivalence.
All right, we're gonna need to move on to some more super chats, or it's not gonna.
Yeah.
All right.
Otherwise not
Melodic Lyrics says Flatzoid's inability to realize that a zoomed in curve is a straight line is so frustrating. There you go.
Let's put it this way: even if it's zoomed in, doesn't make it flat.
All right, go ahead. You got one.
I say, is it a requirement that every heliosexual anti-flat earther must be a narcissist gaslighter?
No. All right. Kuras says, I think we should have Flatzoid cite his Celestial Navigation manual that supports his claims. Title, author, and page number. That's a good one. That's a good one. The one I have so far, the one you gave me doesn't help you. It talks about the Earth being a globe. Sorry.
I gave 7 citations that all say we use
Could
trigonometry.
you email me? Could you email me those or send those to me in Discord?
Yeah, I'll give them.
Cool. All right.
Awesome clips. Thank you very much. And the next one is Lumpy Gas and Vacuum. Thank you very much for your super chat. It says only Globus say straight lines unnecessary.
Only at the intersect, of course. Randomly Epic says tonight's special is a word salad followed by waffle topped with freshly picked cherries that pairs beautifully with a nice wine. I'd prefer the Toonshine. Thank
you. Rob Keane says, thank you for being a member for 10 months. Toon is not winning me back to the globe.
Wasn't my goal. Kira says, what if I have an 80-degree arc on a sextant?
Wow. So that means that 80-degree arc is based from 2 straight lines giving that arc reading?
No, but you were talking about 60. So what if he has it's not really a sextant anymore if you can read 80.
It's 80, yeah.
But what if somebody made a sextant is like, screw the sextant, I'm going to make it read all the way up to 90. Then what?
Okay, mate. If they just change the calculations then. It's not times 60 anymore.
But it doesn't sum to 180 anymore.
Then it's not time. Well, you get sextants that are just to 100 degrees on the index arm. Didn't you know that? Or 140. They're not all 120.
Yeah, they don't. Yeah. But then they don't sum to 180 anymore.
Not all of them, no.
All right, go ahead.
Anyway, Lumpy Gas and Vacuum again for $2. McCringe.
Oh, I'm hurt, Lumpy. I'm hurt, Lumpy. All right, Randomly Epic says, ask Flatzoid how 1 degree per 60 nautical miles is possible on a flat Earth using only straight lines, since that is what he claims.
They do only use straight lines.
But how's it possible?
That's the sextant principle.
It goes back to that.
I explained it. Yeah, angles in succession. If you pick up a sextant, maybe go look through how the mechanics of a sextant works. Very simple stuff.
Oh my gosh. All right.
LJ, ask me Toon if he has nightmares about Alex Stein.
Poor Alex. They both Amy and James apologized to me afterwards. So there you go. Let's see. Holy Smalls says, does Flatzoid not realize that a triangle needs 3 sides?
Sorry? Triangle needs 3 sides, obviously, yeah.
All right.
And then Retro Bull, thank you very much. He says, add a home the day. Flats try claiming that claiming that celestial navigation triangles include an all-seeing eye in the center, and McMason may change his McToon. What?
McMason, that's a new one. I tell you, before this flat Earth stuff, I knew the only time I'd ever seen or heard anything about Masons was the one time we were at a wedding in a hotel, and they were like meeting in a separate meeting room like nearby. I'm like, who are these guys with funny hats?
Yeah, they do have weird attire.
Grumpy Old Mechanic is the one that offered you $500 to go read 20 to the live stream 20 abstracts from 2 specific journals. Says he must include a legible image of first pages. He has 30 days. So there you go. You have the month of September, which has.
Is he going to supply those to me?
Supply what? You go to your local library or university.
I thought he's going to supply the papers to me. I don't have time to look for papers.
Right,
now he's going to say I'm reading the wrong papers.
I'll read again. I will pay Flatzoid $500 to go to his local university library and read the abstracts of 20 papers, each from the Journal of Astronomy and Astrophysics and the Journal of Geophysical Research. He must live stream. That's 40.
I can do it online.
That's 40
I can do
papers.
it online, but I can't do it here because we don't have a university. I'm in the bush.
You don't have a university?
Not where I am. We're in the bush.
All right. How far?
4 hours. I'm like 4 hours away.
So that's a long trip. Do you never get into the big city?
Yeah, I've got family, but I mean 4 hours drive just to go to university.
What is the big city? I don't know. I don't dox yourself, but like, what is the big city that is the 4 hours away big city?
Pretoria, Joburg,
okay,
Johannesburg, maybe. Yeah, Pretoria.
Okay.
They're in between, practically. One's an hour earlier. So
okay.
Yeah, 3 hours actually.
So another thing, if any of the 5, now 4 living people that I issued the $10,000 Southern flight challenges to say yes, and we do take the Sydney to Johannesburg route, will you meet me there and we can meet in person?
Sydney to Johannesburg route. You want to fly?
Yeah. So I have a challenge to Dubé, Jaron, Sargent, Nodell, who's no longer with us, and Dearth, to take a Southern Hemisphere route with me. There's about 5 or 6 or handful of where the flights are strictly in the Southern Hemisphere going between continents, right? Because generally they say that these flights don't exist, and so my challenge to them is we'll ride the flight together, and if it crosses the equator, then they win, and if it doesn't cross and it takes the right amount of time as predicted by the globe, then I win, and winner gets 10,000. None have taken it, but if one of them does, we should meet. How about that?
Yeah, they should do it. Yeah, let them do it. Okay, LJ, explain the fantasy space shuttle travel at 17,500 miles an hour.
It goes 17,500 miles an hour. Why is that a problem? Okay. I don't know why that's a problem.
Okay, but we got to end here because, wow, it's getting late.
All right.
So, any closing sentiments?
Thanks. And we'll do another next month.
Yeah, it was fun.
Oh, one more. Don't let me Flatzoid people. Don't let me be the big patron. You be the big patron. There you go.
But that was fun though. Appreciate it.
All right. We'll see you later.
Cheers, guys, and thanks to you guys on McToon's side.
All right.
I'm sure I won't read the chats.
All right, dude. We'll see you.
Okay. Cheers.
All right. Let me roll back to a few of these that I skipped. Nike Spitz, or says it's Nikkei, says this time is much better for me now. I can watch live. Happy me, and I already know he will destroy Flatzoid. And as usual, I may add. Thank you. Elliot Dan Garris, I've not seen before, says first time catching one of your debates live, enjoying it so far. Well, thank you very much for that, Elliot. All right, jumping ahead to, I got a few. Cretan Bulls has got a lie to flurf. This is embarrassing. It is. We got Cygnus Step says horizontal baseline. He didn't say that. He tried to. But just for reference, he can't do celestial navigation. No flat earther can. If they could, they would have already. Right? And he's like, oh, I didn't do it because, well, why not? No good reason. If he had a good reason to do it, to not do it, he would have done it, right? If it was possible, he claimed it's possible, then he would have done the challenge that I put out there. And he would have been crying over and over and over if I didn't pay, right? But they didn't even do it. No flat earther has done it. It's not possible. That's why. Melodic Lyric says Trig is circles, Flatzoid. Trig is a lot. There's circles in, yeah. But he just kept going about SOHCAHTOA, which is triangles, which is part of trigonometry. So, Second Best Bob says, love to have Toon live when I'm awake in the UK. I like doing it a little early. I'll wrap up a little earlier. And I got a bunch of other stuff to do today I might get to. Serena's1 says, I nominate Flatzoid for Dip of the Horizon. Yeah, too bad I couldn't live pull up the derivation of that. But no doubt the radius or circumference, probably radius of the Earth, is involved in that 1 point. Move the paper. 1 point one. I don't know. It's on here. Hold on. I'll pull it up. I'll find it. 1.753 times the square root of the observer's height in meters, I believe. Mikey Riot says, I'm donating 50 angular linear % of this 5 Great British pounds to Flatzoid's caretakers so they can buy a better stair/baby gate. Oh, I like poking his patrons. Lenchoman is a new member at Newton. Thank you for that. Serena's1 says, fools rush in where angels fear to tread. That's a line from a song I like too, by Deliverance. Find that one, people. Find that song. The grumpy old mechanic said, if I supplied the papers, he would claim fake. Of course he would. Yeah, he needs to. It makes sense that he should just go there himself and pick them. Dude, for $500, I'd drive 3 hours one direction and read and learn. Yes. But he won't anyway. Pat in the chat says, your next Patreon payment for Flatzoid is on me. This was absolutely hilarious. Looking forward to more. Thank you for that. Yeah, if you're interested in what the topic should be, because he always wants me to pick the topic, then let me know. I have some ideas, but if you have them, probably gravity. That's my next one. Unless Pat or somebody says it should be something else. Okay, Marza said the radius is involved in the dip of the horizon. I already tagged you on your Discord with that derivation. Okay, could you DM it to me? Because I get too many tags in regular chat that I miss them. The number of notifications I have, I actually turn it off, but I have 116 on notifications on my own Discord server, 898 on FTFEs. Sparky Steve says, I'm surprised Flats has shown his face again here after his last perspective showing with you. Flurf reset in full show. Oh my gosh, yeah. And he has his flask challenge he likes to talk about. He was trying to remember when he said, is that orthographic? Is that orthographic? He was trying to get onto the flask challenge. The flask challenge is deception. He lied about the distances and he lied about the angular measurements that he did there. Sloppy. So that's why it doesn't work, right? He gives it to everybody. He's like, aha, you can't figure it out. The reason why is because he did crap measurements. Sparky Steve says, Flatzoid's derp is super tangy. Left a taste. Ugh. Oh, here we go. Here's Walter Bislin. Says dip angle equals square root of 2 times 1 minus k divided by r times 10,080 divided by pi times square root of h equals 1.753. There it is. I'm gonna grab that and hold on. I gotta put that. I'll just send that to him. He won't like that. Thank you for that, Walter Bislin. Anyway, that was for 10 CHFs. CHF. What currency is CHF? Swiss francs. Ah, very nice. I know that he speaks German. I didn't know where. All right. MB for 2 pounds is first law of Flurf confirmed to infinity by Flatzoid. Yes. It's like it's right there. Everything, and nowhere. Oh, I can't believe. Like he actually thought that having just like a trigonometry review somehow meant that they were doing celestial navigation using triangles. That's not how it works. Oh my gosh. Hira says when we were talking about nautical navigation, we were talking about sextants. Flatzoid, you've never used a sextant to perform celestial navigation. He's never performed celestial navigation. Nor has he used a sextant, nor has he done the all he did, he keeps showing those triangles, right? Where he's like subtracting that. But here's the problem. And he doesn't get this. He doesn't get this. When you use that 60 nautical miles that he has no derivation for, it tells you the mandatory height of the star over flat Earth. But it's different for every single distance from the star. It fails. And he doesn't get that. And his only thing is Flask. Flask challenge. Turing Test 2 has a super chat for 10 pounds, but no message. Thank you for that, Turing Test 2. Faju _E is a new member at Newton. Thank you. And then Elliot Dan Giris is a member as well at Newton. We got FST first one niece for 50 secs says this is so painful. What's a strange bunch of self-tormentor we have with Toon himself as the leader. Right? Letting a flat earther just show how ridiculous they are is hopefully shows somebody else might just happen along and say, dear me, how can they be that dumb? That's not possible. Citizen 9 is a member at Newton, says, here we go, folks, flat nav. No, he didn't show it. He never showed it. Nick N is a new member at Newton. RT96 says, I used a sextant to measure the angular separation betwixt the top and bottom of my monitor. It was 10 degrees times 60 miles equals 600 mile tall monitor. Absolutely. He thinks somehow a sextant has built into it 60 nautical miles somehow. Right? And somehow he thinks that because it's 60 degrees, it's 60 nautical miles. Like there's some relationship he thinks there. No, of course not. And that's why Kuros's question, what if there's 80 degrees in it instead of 60? Is it 80 nautical miles per degree? He must think that. String News 1, show us your sextant Flatzoid. We don't want to see his. Oh, it sounds a little too naughty. Danger Bear says, please tell Flats he can do F all with an angle. Yeah, he has no idea. He has no idea at all. Lentomanin says, thanks for bringing the laughs, MC2, keep it up. Thank you for that. And Grumpy Old Mechanic says, if I supplied the papers, he would claim fake. So he has pretty much already rejected your claim or your offer. For somebody in South Africa, in the bush, as he says, that's a pretty serious amount of money. I can't believe it. Dave Kircher says, redacted witty caca. It's Wounds Day. Thanks, Dave Kircher. And Radek Staniski, this is Radek's first super chat, says, I was so hyped to finally hear how to get 60 nautical miles per degree on flat Earth. No. Oh, nay, you will not be getting that. And of course, that is one of the things that would need to be done for celestial navigation using only flat Earth, is showing how 60 nautical miles per degree was derived without using the circumference of the globe, which is, he knows, they all know, is something they cannot do. Henrik Danielson says, I just learned from a flurfer, there can be only one programmer. Highlander rules apply. Charlie, you let him off. He never did explain the relationship between angles and miles. I know, but I kept pressing him over and over and over again. I mean, how many times could I press him? Right? Yep. I let him off. There's the thing is, it's just the infinite demanding that he say the same thing over and over again. He showed that he cannot provide the relationship between 60 nautical miles and any angular measurement. He cannot do that. The fact that all he did was say that it's 60 nautical miles per degree every time I asked him shows everybody watching that it's not possible. Right? Think about this. I at some point, he will have to, it can't happen. We all know that the derivation of that is from the radius, the circumference of the globe. He knows that too. He knows that too. And so he knows he can't ever do that. So, Citizen 9 is looking forward to Flatzoid's review of the debate. Oh, yes. That will be good. All right. Mazda. I have 140 degrees on my sextant. There you go. What's 140 degrees plus 60? It's not 180. Seriously, he thought that because one part of a sextant was 60 degrees and another part of a sextant was 120 degrees, that since they sum to 180 degrees, that there's a triangle somewhere. Talking about, whoa, man, affirming the consequent, right? There's 180 degrees in a triangle. That has 180 degrees, therefore it's a triangle, affirming the consequent. The broken trifold says, you must have seen his face. He was totally thinking he was destroying it. Yeah, he totally thought so. That's the Dunning-Kruger. That's why I'm very sad that he didn't win this year. Next year. You could, Jeebus says, you could ask him to place the conveniently sized celestial sphere on a flat Earth map. We know distances on Earth the celestial sphere won't fit. Yeah. Oh yeah, he's already bragging he was right on the channel. Anyway, people, thank you very much for this this little unusually timed one. I don't have anybody for next week, so if you're interested, so it might be Discord. I go to Discord. If it is Discord, I might be introducing a new thing. Be ready for that. I use Discord like what's his name? Apocryphon wants me to go every other week. I'm like, I don't know. Should I? Do you like to see it every other week? Is that enough? So, question for you. Anyway, people, thank you very much for participating, for joining, for super chats, for members, for being patrons, so that I can be Flatzoid's patron and basically give him a little bit, and then also poke at his supporters so that they might maybe take a little bit of money away from some other flat earther and give it to you know what I'm talking about. Give it to Flatzoid instead, which I think is an improvement. But we'll see you next time, everybody. Stringer News 1. I'd be on Patreon, but I spent it on Patron.